So we have about 9 people here, maybe 8 people. So that's perfect. Good morning. Thank you for being here. Thank you for all the donations. So I just wanted to thank everyone for donations and talk a little bit about Team Mercy. Yeah, actually, before we do that, let me introduce myself. I am Yusuf. I am working as a data scientist with Engin in a company called Signify Health. We love data science, and we always wanted to share our love of data science with others. And thanks to Murali, Murali provided a really nice environment for us to get together and cover data science topics. So a big round of applause for Murali for setting everything up here for us. So today's schedule is for the first half, we're going to cover linear regression, logistic regression, and decision trees. These are really big, very common machine learning models. So once you understand these, you're gonna be ready for the second half of this data science workshop, and you're gonna be ready for all kinds of future machine learning models. So make sure you understand these models well. Then you're gonna be able to build on top of those really, really easily. So before we begin, let me share my screen real quick. Here. So Team Mercy is a nonprofit organization named after Mercy. Mercy was born in 2011 and died after 13 days. So 13 days was a really short time. It left a trauma on the siblings. So what the parents did is they founded, the Ellison and Rodney founded this organization, Team, and they're helping kids who lost their siblings. So they give donations, they do gifts. So they're basically trying to make their dream come true. So, all of your donations are going to be spent for good. A little bit of highlight here. Then I like to start with this tiny little data set. So basically, I have already shared this data set with you in the comments section. So let me know if everybody is able to open it. So the data set itself is not like super interesting, but it's gonna give us a very broad introduction of the three models that we're gonna cover today. So linear regression, logistic regression, and decision trees. So imagine we have this kind of problem. So we have this data. We know the square foot of the houses. We know the square foot of the houses. This is in thousand. 1,000 square feet is sold for 120,000. So we know that. And it is sold within 30 days? No. So it is 0 for no, 1 for yes. 2,000 square feet house and sold for 190,000, and it's not sold within 30 days here. So we have 4 data points here. So let's say we want to understand the relationship between square feet and sales price. For this, we have to look. We have to have some sort of a formula that takes square feet and applies it to sales price and comes up with a formula. One way we can do is linear regression. So since this is a continuous variable, we can apply linear regression. So let me show you how it really looks like. So if I select these two, do a scatter plot, I'm gonna just name it linear. So you can see that there is a certain trend here. So as the square foot increases, the sales price is also increases. So these are the type of patterns we are trying to capture in a machine learning model. So what linear regression does is it fits a line between the square foot here and the sales price here. So let me draw it. It's a really nice line here. So fitting a straight line is the basic idea behind linear regression, and we're gonna hands-on apply it in Python in just a second. But this is linear regression, a very broad perspective. Okay, so let's say the second problem is we want to predict, instead of sales price, we want to predict whether the house is going to be sold within 30 days. As you can see, this data is a little bit different from this type of data. This has either 0 or 1. So this is what we call dichotomous variable or dummy variable. So it takes only values of 0 or 1. So if the data is something like this one, we cannot apply linear regression. We have to be creative and use a classification model. And in this case, logistic regression is going to help us. So let's first visualize it, how the relationship looks. I'm basically putting it here. So this is the model. As you can see, this is different. So the values is right next to each other. So these values can only take the value of 0 or 1. So in here, 0 or 1. So we cannot fit a straight line here. So in logistic regression, we have to fit a line that do not exceed above 1, and it doesn't go below 0. So what logistic regression does is it fits a curved line. And a curved line looks something like this. So what logistic regression does is it estimates all the probabilities given a value of x. So this line is always square feet. This x vector is always the square feet. Okay, that being said, okay, well, maybe I don't want this complicated model. Maybe I want to have a very simple solution for the second problem. I'm gonna predict whether the house is gonna be sold within 30 days. And as you can see here, if the square feet increases up to a point in right here, house is sold. So right here, it is sold. So we have this section of data, and we have this section of data. So in a decision tree algorithm, what I can do is I can put a criteria. It is like an if statement. So if the square foot goes above a certain value, I can say that the house is going to be sold. So in this case, around 2,500 is a really good estimate. So if the house is above 2,500, I can say that the house is going to be sold. So this is what it looks like. So I have a variable called here, sold. I should have typed it. Okay, so this is sold as a variable. And this is my decision tree. It is below 2,500. I can say that 0, I'm going to predict 0. If it's below 2,500, above 2,500, I'm going to predict 1. So this is the basic idea of decision tree. Let me sort of title it. So these are 3 models that we're going to cover. So we're going to have hands-on exercise in right away. So these are 3 big models. I can take questions, then I'm going to shift to Python, and we're going to do some hands-on. So I don't expect you to repeat it, all this process, but I want you to have a very broad understanding. Once you have this broad understanding, then you're going to understand the Python code so much more easily. This is really, so it is okay if you didn't totally understand it, but at least it's good to have some sort of exposure before we start the Python code, because I don't want you to get lost in the beginning of the Python code. So, any questions?
Hi. Hello, can you hear me?
Yes.
Hey, first of all, thanks to you. Thanks, Yusuf, and thanks, Murli. I know it's a weekend. Thanks for spending time. I'm a nerd. I don't know anything about data science. This is good to start with, but when should you use, like you took the same example of this real estate and showed these 3 models, like linear and logistic, when to use and which is more appropriate? How do we know?
Yeah, absolutely. So the first thing we're going to cover in just a second. The first question you have to ask yourself is whether your problem is a classification problem or a regression problem. So classification problem is when your outcome variable in here has a dichotomous variable like this. It is either 0 or 1. So let me do here. So this is outcome. This is another outcome, and this is a predictor. So I'm gonna come back to this in the Python code. But basically, so this is one outcome. So this is sales price that we're gonna predict. So as you can see, it can take any value here, any value from minus infinite to plus infinite. So it can take any values for a continuous variable in here. So the house price could be 0, or it could be 10 million, 100 million, 1 billion. So there is no upper limit for this one, for this variable as an outcome variable. But for this type of outcome, we have only two classes. So it is either 0 or 1. So 1 is usually the variable, the data point that we are interested in. So it can only take the value of either 0 or 1. So basically we are forcing the data to be in one of these buckets. In this case, I'm going to come back to this in Notebook, and it's going to make more sense with more examples. So this is the first thing you have to ask, whether that's a classification problem or a regression problem. If it's a regression problem, you can apply linear regression, and you can also apply decision tree. If it's a classification problem like this, you can apply logistic regression.
Okay, thank you.
I'm gonna actually drop from this machine. This is a Windows machine. Then I'm gonna shift to my Mac. So it is enough exposure of Windows machine for me. I'm gonna stop sharing this screen now. All right. I'm now here in the other machine. I hope you can hear me. Okay. So is the voice is better now?
Yeah, it's actually much better, Yusuf, now. I think on the previous machine, there was a little bit of a mumbling.
Okay, yeah, I'm
much
sorry
better.
about that. So it would be really great if you just click on this link here. So this is a link for Teaching for Good first half Python notebooks. So what you should do is you should go ahead and click here, and you should add it into your own drive. So I can see that link here, but let me log in with this guy. So once you see this, so I'm clicking on here. All right. So once you open it, you just click here, and you have to add it to your My Drive. Just click on here and add it to your own drive. Just click on Add to My Drive, and you're going to be able to find it under your here, under your folder, My Drive, and under your folder, you can find it. So please just go ahead and do that, because you're going to start running. So can I get a confirmation that you all added this to your My Drive? So the link is here, right here. So this is the link, the first link. Yes. Okay, so once you add it, you can click on the first notebook here. So does everybody see this? You should just click on it and it should open the notebook. So it should open it through Google Colab. So it might ask you to download the plugin for Google Colab. So in the plugin page, you can open the Google Colab. So what basically works is, how it really works is, Google opens a virtual machine for you. It opens a really tiny cluster for you to run Python code. So Python is going to be already installed in that environment, and you're going to be able to run it without installing anything into your machine. So you're going to be able to run Python code in Google Drive. I'm going to wait for a second for everyone to open it. So please don't forget to add it into your own drive. So it should be, the option should be right here. I'm gonna remove it again. So it is under shared with me. So it is under shared with me, shared with me folder. I click on it and it's right here, add to my drive. So to be able to open it with Google Cloud, you will need the Google Colab plugin if you don't already have it. When you right click on it, it's going to give you the options of adding Google Colab. So adding option is here. So I'm going to add it again. Okay, it's here. So I'm right click on it. I'm going to open with. So once I added it, I'm going to right click, open with. So I see Google Collaboratory here. But if you don't see it, here is how you add it. So click on connect more apps and search for Collab. In this case, I think it doesn't show up because I already have it. It's under Collab here.
Yeah, with single L. Just one L there. It's a collab.
Okay. Yeah. Okay, there you go. So when you see Collab, you find it here. You just click on it and click on here. It's gonna say add or something or connect. You just click on it and you will add collaboratory. Once you add it, everything else is Google, so we're not going to install anything else. So I am going back again. So I installed it to my OneDrive, so my drive. So it should say my drive here. And do right click, open with, connect more apps, and collab. Search for collab, and collab is here. I click on it and add it. So can I get a confirmation that everybody is able to do this? Because without this, you're not going to be able to run Python, and you're not going to be able to open the notebook, probably. But once you do it, this is everything you will need. Okay, awesome. So Kash, were you able to do it? The IRC, Megan, Ranjit.
It opened with Google Collaborator with linear regression. Is it the right one?
Yes.
Okay.
Yusuf, thanks for
Yeah.
everything so far. I'm gonna let you know I'm being a bad student today though, because I am painting a room and listening and learning as I'm painting. So I'm not gonna be doing the hands-on, but I'm still learning and listening along the way. So thank you.
Awesome. Thank you for participating.
Yeah, this is really great. Thanks, Yusuf, for taking time on the weekend and helping us learn some insights on these machine learning things.
Absolutely. Okay. If you need any help, you can always reach the Murali or Engin. So I wouldn't really want you to lag behind.
Yeah, go ahead, Yusuf. We will take care of moderating on the chat window if somebody needs help.
Okay, awesome. So I'm gonna close it. I'm gonna close it. So once you click on it, right click, collaboratory. You will see this open in Playground. So it is in viewing format now. So for you to be able to run it, you have to open it in your own cluster, basically. You just click on open in Playground.
So, a question, Yusuf, before we start playing with all these things. What's happening here? So we are on the drive. You got your code on the drive on the Google Cloud. By the way, this is Ranjit. Sorry. So on the Google Cloud, so what does this collab do?
Absolutely, that's a really good question. Very general. So, so Python is a language. So as everybody knows, so
Right.
you should be able to run it with a machine. So there needs to be a computer behind that computes everything, and there needs to be an IDE, so the editor, for you to be able to communicate with Python. So one of the most common editors is Python Notebook. So it has this extension here, IPython Notebook here. So this is Python Notebook. And for you to be able to run it, you have to connect with Python. And this is basically an editor, and this allows you to run Python codes in it. And what Google Colab does is, instead of installing everything into your local machine and installing all the libraries, which is going to take some time, this handles everything on the infrastructure side. So it opens a really small cluster for you, and it allows you to use it. So actually,
so would this be a community edition, or if it has to be used to the corporate level, has to be licensed?
excuse me, I didn't understand.
So I know that we are today learning on this, but let's say if you were to use for the real practical solutions at your production environment, should this has to go to the licensing logistics and all?
No. Python notebooks are used for development purposes, and this is actually what we use in the company as well. So we are using Python notebooks. There is no licensing, nothing associated with it. Everything is open source, free, and this is actually where we run it. Instead, we are not connecting to Google. We are running it in our local machine.
Okay.
Does that answer your question, or did I miss it?
Yeah, it did. It did answer this. Thanks.
Yeah. Ranjit, to add to that, if you want to run it in production, the initial cluster that you are getting in the community edition is not enough to process all the data. So you will have option to connect to Google Cloud and actually spin a much bigger cluster, still connected to the same notebook if you want. So it is possible to connect to a much bigger cluster in the cloud. But this notebook as it is, it has a small cluster already connected so that you can actually run and test your notebook. And it's for free, so that's why they just included a microkernel there. But it is possible if you want to use it in production, you can connect to a much bigger cloud and process a much bigger data set.
Okay, got it. So that eventually would probably have to go through the procurement of these Google Cloud cluster, right? That's what I meant earlier.
That's correct.
Yeah, thanks.
So once you open it, there needs to be something like connect. It should say connect here, right here, and click on it and connect. So first you should have clicked on open in playground somewhere in here, then you click on connect, then you are connected. So as you can see here, it says Python 3 Google Compute Engine backend. Google gave us a basically a computer in 0.63 gigabyte RAM and some disk. So here you should click on it, and then you will be able to, you will have connected. So everybody should see this on the right hand. So this is important because otherwise it's not going to allow you to run it. So this is the last thing we did.
Is it similar to Amazon SageMaker or something?
Excuse me?
This particular playground environment, is it similar to Amazon SageMaker or something?
Well, I'm not very knowledgeable on that side, but it is just a machine, very tiny little machine on there in Google. If anyone is knowledgeable about Amazon SageMaker, you can let us know.
I can answer. This is Murli. Yeah, SageMaker also provides a notebook environment, notebook interface, but SageMaker does do lots of other stuff as well. Essentially, what Colab is doing is it provides this notebook environment. To be able to execute this notebook, you need to have the Python environment on the back end. Either you can install it on your local machine, or Google actually, in this case, Google provides that machine on the in the cloud and connect that machine with this notebook, so you can actually run it directly within your browser without having to install anything. But you can actually install the Python environment on your machine and open this Jupyter notebook on your local machine as well. That is also possible. There are lots of companies offer this environment, the similar notebook environment, if not exactly the same. But most of these companies provide the environment, and the underlying technology is always called as a Jupyter notebook. Jupyter is the name of the product. It's an open source notebook product. Anybody can use it. And many companies actually offer this service. Even Azure has it, Google has it, Microsoft has it, as well as there are other third-party providers as well that offer this service, so that people can run these notebooks in the browser without having to install as part of learning. But when you want to go into production, of course, you will use this notebook but on the back end, you will probably replace with a much bigger data set, much bigger machine or a cluster of machines.
Thanks, Murli.
Okay, so if you already did it, then we can go ahead and start with our notebook. So we have the infrastructure ready, so we can move on. So Jupyter Notebook is really nice. You can it works with cells. So each one of these are cells, individual cells, and these cells can either be marked down or Python code. So you can either add a code or a text. So if I add a code, I can run it. Then I can add a text. I can write text, and it will show here. So it goes cell by cell. So this is the linear regression section, and it goes all the way back to the first question. So we have, how do we start? How do we select the model? So we have two types of problems. One problem is classification problem. The other one is regression problem. So two problems. So every machine learning, this supervised learning problem has two types of problems, either categorical response or continuous response. So for example, if you have to predict someone's age is a continuous variable. It can range from 0 to say 100. So it can take any value in between those. So it is a continuous variable. So it is continuous response. So if I had to predict someone's age, then I will have to use regression here. Regression problem. But if I had to select if my team is gonna win the game tonight, for example, then I would have to run classification problem. So team is either gonna win or lose. So imagine NBA finals. So either one of the teams is gonna win or not. It is 0 or 1. So it's a categorical response. We have to force our response to be in either one of those categories. So basically we get the probability score and we code it, we force it to either 1 or 0, and we're gonna come to that point. So linear regression is about continuous variable, and it's a regression problem. Don't get confused. Logistic regression, although it says regression, is not a regression problem. Logistic regression is a classification problem. So it's a really important note there. So once we run it, you're gonna understand it better. So in Python, if you already use any software, we have libraries, and this is how we install it. So if you come here and click on it, so it's gonna say the notebook was not authored by Google. It basically gives a warning for you. After you click, just say run anyway on here. Run anyway. Reset all run times, yes. It's just a warning, but it's not very important. So we imported our library here, and we imported our visualization library. So let's start with a case problem. So we have, we want to advertise. So we have an advertising data here, advertising CSV. So here we import it and we look at the data in this code. So in this case, sales is our outcome. So basically what we're trying to do is we want to increase the sales. And to be able to increase the sales, we make advertisements on TV, radio, or a newspaper. So we want to know which one has the most effect or which one is effective, and then we want to invest in those areas. So if TV is more effective and we want to see if they're spending any money on advertising on TV is effective on our sales. So we have these data points. So here in the head statement, we only see the first 5 columns. If you come here and open another cell, and if you do ADC, it's going to show as much as data as possible here. So this is our data. It's our entire data here. So these are our columns, these are our variables, and sales is our outcome variable. How do we know that it's outcome? By basically a theory. So basically, TV advertisements cannot predict, can predict sales, but sales cannot predict TV advertisements. So basically, it's a cause and effect relationship. So basically, what we're trying to do is to increase sales. And first of all, we want to see if there is a relationship. And we want to understand data a little bit. Then we run this code here at shape. And it basically says that we have 200 rows here. If we go all the way down, it is 200. And it says we have 4 variables. It says 1, 2, 3, 4. We have 4 variables. With the shape statement, this is what it does. So basically, we have 200 markets in the data set. Each row is a market. The features are TV, radio, and newspaper advertisements. Our response is sales here. So we want to answer to the question, is there a relationship between ads and sales? How strong is the relationship? Which ad type contribute to sales? And what is the effect of each ad to sales? And given ad spending in a particular market, we want to predict the sales. So after we run it and we train our model, we're going to predict, we can estimate our future sales. So just like we did in Excel, we're going to run a scatter plot. So this is a scatter plot. Basically, on the X column, it is the independent variable or the predictor variable. Basically, this is TV advertisements, radio or newspaper, and these are the sales. As you can see, there is actually a trend here. So as TV advertisements increase, as we spend more time, more money on TV, then our sales actually increases, as you can see here. So you can say that there is a relationship. So as one increases, the other one is also increases for TV. But this one is a little bit less clear, but still you can say that there is a relationship. So as radio increases, the sales are increasing. The newspaper is not as clear as the other ones. So we cannot quite say that if there is a relationship. And the way for us to be able to know it is to run a linear regression model. But we're going to come to that. So we can include a regression line into this plot. We can run it. And we edit this regression line here. And in here. So what regression line is, it is the best line possible, best straight line possible in the model that explains the relationship between these two variables. So on the background, linear regression tries multiple lines and it fits the line that is the best here. So this line becomes our formula at the end. So we mathematically represent this line, and this becomes our model. And if we have to predict anything in the future, we just use this line. So what this line is saying is that, for example, for $50,000 sales in TV is associated with somewhere in here for $9,000, for example, sales. So 50-point TV advertisement is associated with about 9-point sales. So let me move a little bit forward. It's gonna make a lot of make sense. So we can visualize the relationship between all the variables on here. This is the data exploration section of data science. So once you get the data, you want to look at all the kinds of relationships. So it is between all the variables to the other variables. What we're interested is actually this line here. So we already have seen this. So this one section here, TV, radio, newspaper to sales, we already seen this part. But we want to also look at the other ones just to see if there's a correlation between the other predictor variables. So this section is symmetrical. So as we can see that between newspaper sales and radio, for example, there's not much of a relationship, which is good. Also, we can look at the distributions of each of these columns. Then we can fit a regression line with this argument here. So it is the same code. We just added kind equals reg. So it shows that there is a relationship between newspaper, radio, TV to sales. Sales is our outcome variable here. And we to mathematically represent all these relationships, intercorrelated relationships, we run the correlation matrix. So the idea behind correlation matrix is it stands on the linear regression assumption. So basically in linear regression, we assume that there is not a strong relationship between the predictor variables. So predictor variables are these: TV, radio, and newspaper. So for us to be able to correctly use all of these in the same model, there should not be any relationship between, interrelationship between these predicted variables. So like this one. So as the radio sales increase here, newspaper ads also increase. So there's a line, it's a positive. So we don't know if we should worry about it. So if you look at here, the correlation number is 0.35. So it's just a value. It ranges from 0 to 1. We should only be concerned when the value is above 0.7. So since it's not above 0.7, then we are good. So this is an assumption in linear regression. For other types of regression problems, so you don't have to worry about correlation between the variables. So we can also run a heat map here. And this pretty much concludes our exploratory data analysis section in here. And we're going to start with the actual linear regression in right here. But before I shift to the next part, I want to see if there's any questions. So I know it's a little bit confusing at this point, but the general point is here. So fitting the regression line. So what you need to remember from this section is this slide here. So this is important. So this connects to the Excel file we just did. Yeah, please go ahead. Any questions? It's lots of information. So, yeah.
Question here, please. So when it goes to the correlation matrix, why is it required to have the relation between other elements like TV versus radio or TV versus newspaper, when actually we are looking only to have a relation between the sales versus TV, or sales versus radio, or sales versus newspaper, right?
Yes, exactly. So this is a linear regression assumption. So it's a theoretical assumption. It says that there should not be any strong correlation between the predictor variables. TV, radio, and newspaper, there should not be any relationship. So the idea is this. So instead of predicting the sales, these variables are going to predict each other in the model if we put them in the same model. And we're going to be using basically the same variable twice. So in this case, we don't have a lot of correlation because they are actually different variables from each other. So usually the correlation happens in variables such as like birthday, for example, birthday date and your age, for example. Your age and your birth date is highly correlated. It's the same thing. And you cannot use the two variables at the same time. And it's going to screw up the coefficients that we're going to just cover here. The regression coefficient is going to screw all of them up. And your predictions are going to be all wrong. So linear regression is a very simple model here. Like this one, you just draw a line and you explain the relationship. But it comes with lots of assumptions, and one of them is that there should not be any correlation between predictor variables. So that's one big assumption. So
okay, thank you. So coming to the same point, earlier in our discussion, we thought that if the relation between these predictor variables is above 0.7 or 0.75, then there is something that we need to consider. So if you go back down in the correlation matrix again, there is a relation between the TV and on the sales, where it is above 0.78. So should we need to consider that by any chance?
yeah, that's a really good question. So we are not concerned about that because that's a correlation between TV and the outcome variable. So this is sales. So this is actually what we want. We want the other variables, the predictor variables, to be highly correlated with sales. It just basically explains this point here. It's just basically saying that as TV increases, sales strongly increases. So this is good. So any value that has to do with sales or the outcome variable, we are not concerned. So we're not concerned about this or this or this or this. So these three values we're not concerned about. But that's a really good question. But I hope it answered your question.
Yeah, it did. Thanks. Yeah. So that's true. Only the TV and sales amongst this entire graph or chart is having more than 0.75. Otherwise, the rest everything else is under
0.7?
Under 0.6. Yeah.
0.6. Yeah, it doesn't matter. That's good.
Yeah.
Okay, let's go ahead and fit a regression. So basically, so for us to be able to say that we have a linear regression model, we have to mathematically represent this line here, this line. So this line has two components. So one of them is the point, it crosses the y line. So it crosses at 6, for example, in here. This is called the intercept, this point right here, the intercept point, and the slope. Slope is the other argument in linear regression. So we have two arguments. So given that y is the response and x is the feature, b0 becomes the intercept, and b1, beta 1 is the coefficient. So we can take these two values and we can represent our model just like this one here. So this becomes our formula. So we're gonna come to that after we fit it. So what is it really saying? What is it all about? And we're gonna learn it after we fit the model. So here we take the TV as a feature column, and we select TV column here, and we prepare the data for us to be able to fit it. The coefficient represents the slope. It represents the slope between the TV and sales. So this is the angle. So for example, for a 1 unit increase from 0 to 1, how much of an increase do we expect in sales? So that's what coefficient is. And in the interpretation, we're going to come to that in just a second. So let's first fit the model. Once we fit it, we can print the intercept and we can print the coefficient. So basically this becomes our formula here. I can add a text here. And this is X. So this is our formula. So this is the intercept point. This is the point the line crosses the y vector. And this is the angle of the line, basically. This is coefficient, and this is the intercept. This is the intercept point. It crosses at 7, unit 7. And this is the angle. And the interpretation is we're gonna come here. Okay, so interpretation is this. So how do we interpret it, the coefficient, and what it really is? It is this. It is a representation of 1 unit increase in TV ad spending, and its association with unit increase in sales. 1 unit is basically this. If we do 0 advertisement, for example, today, and tomorrow in another market, if we do 1 unit TV advertisement, if we do 1 unit increase in TV spending, this is how much increase in sales we expect to see. So unit is right here. So basically here. So I have this here for 100. Actually, let me actually do this. So for example, if I will take this formula and basically apply it in Python. So I do 50 units advertisement in sales. So in this formula, this is the coefficient, This is the intercept. We already have it. This is our formula in here. And how do we know it? We get it from our fit model. So this is the intercept, this is the coefficient. Let's say we're trying to estimate if we do 50 unit sales, how much of a advertisement, how much of its sales are we gonna make? If we do 51 unit sales, this is how much of a sales we expect. 51 unit advertisement, and this is the amount we expect to see in sales. If I take this value, here's the coefficient. So basically, I increase my advertisement from 50 to 51. And this is how much of an increase I had. So I increase my, here, 1 unit increase in TV ad spending in here from 50 to 51, associated with this amount, the coefficient amount, unit increase in sales. So I increase my sales from 50 to 51, advertisement from 50 to 51. This is how much of a sales that I predicted. And this increase led to this amount increase in sales, the predicted increase. So it can be, I can do it with also like 0. I can increase from 0 to 1. If I do 0 advertisement, then I expect this amount of sales. If I do 1 unit advertisement, this is the amount I expect. So if I take this value, and here, wait, this is still the same, as you can see. So I increase my advertisement by 1 unit, and this is the amount of increase in sales that I expect. So this is the general idea. I hope it makes it clear. If it's still not clear, I can give more examples.
So a question again here. This is Ranjit. So based on the same formula, if we go down to the data there, for the first row where we have 230 as the data set, as a TV.
Yes.
So if you plug in that value into your formula, then should I not expect the sales as 22.1?
So it's a predictive model. So if I apply this one, I'm gonna see the predicted value and right here. I can actually do that. So this is for the first column. I can copy and bring it all the way down here.
Yeah, I guess it's coming around 17 odd, not 22.1.
Yes, so this is my actual value, but the model is going to predict something else.
All right, so that's just a prediction.
This one, yes, I'm going to take this one, and this value is here is 230.1. Applied, it's 17. Model is estimating 17 or somewhere around 18. So this is my predicted value, but the actual value is 22. So let me show you what this 18 represents. in scatter plot. So my value was around 231, right? It was around here. So if I go all the way up here, this line where it crosses is my predicted value. So it is around 18 here, and this is what model is representing. So this line is my predicted values in here. These are the values that come out of the formula. All these values. But if I go all the way up here, I can see, for example, 21 here. This dot, let's say this represented. This is the actual value, and this line where it crosses is the predicted value. So the gap between this dot and the line is my error. So this is 17, and this is my actual value, 22.1 minus. So I missed it by 4 points. So this is my error. I can say error equals this amount, then I can print error. So this error amount is really important for the linear regression. So this is how we know that our model or our line is a good one. Ultimately, what model is trying to do is to decrease all these errors. It's a really hard job, as you can imagine. So there is not a one single line that can fit everything. So this predicted value should cross everything for us to be say that it perfectly explains the data. But we have only one option. The line has to be straight. It needs to be straight, and it needs to explain as much information as possible. So we take all the dots here, and we're trying to explain it with a simple model, simple formula, very two-line of formula, all this relationship. So it has a big cost there in terms that we lose some of the information here. So we predict that it's here, but actually it is somewhere down here. So we lose this information. We'll lose this information here as well. So linear regression formula here. So the linreg variable here, the assignment here, linreg. We can also use it to predict all these values. We have calculated manually here, but we don't have to do that. So we can write linreg predict, for example, value is 50. We will get the value of this one. So this is the exactly same value we calculated. We had calculated here. So this is the formula. I'm bringing it here. Okay, this is the same value, as you can see. So what this does is it takes the input as 50, for example, as a TV advertisement, and it predicts the outcome. So this is actually the machine learning part. Once you fit the model, you predict something in the future with new data. Let's say we're gonna open to new market and we want to make 50 unit advertisement. Then this is the amount of sales that we estimate to have. Yes, exactly. So there could be multiple predictors. And this is what is called multiple regression, and we're going to come to that actually. So let's cover this one, then we can take a short break. So we can predict 50. It's a reasonable number, but we can also predict 50,000. So if we make 50,000 unit advertisement, this is the amount of sales that we predict in here. And this is a better explanation of the coefficient. That was one of the questions. So 1 unit increase in TV ad spending is associated with this unit increase in sales. It also means that an additional dollar spent on TV, each additional dollar spent on TV is associated with this amount of sales. Again, an additional 1,000 spent on TV sales, and we just multiply it with 1,000. This value of widgets in sales. So just look at it. Just go through it by yourself. We can take maybe 5-10 minutes break, and at the same time you can go over it by yourself. Just run it by yourself and play around and try to understand it. There's a lot of information. Linear regression and logistic regression, they cover it in a semester, and we're trying to cover it in just 1 hour. So it's a lot of information, and it's going to make sense once you apply it by yourself and going through all these documents by yourself, one by one. Okay, maybe let's take a 10-minute, let's call it hands-on. You can take the time to use restroom, or you can take the time to go through all these codes by yourself. Just start here and go through it by yourself. Multiple regression model, multiple linear regression model. So in this outcome, instead of using only TV, we are using radio, we are also using the newspaper. So basically, instead of having 1 coefficient, now we have 3 coefficients. So the coefficient section is the part we are concerned about. This is not very important. This section is not too important. This section one basically says that all these relationships are significant, which is good. So I'm not going to highlight too much what significance is. This is especially important in the academic setting, but this is not so important. People don't seem to be too much worried about regression in data science, significant test in data science. And so this section is important, the adjusted R-square. So these are the model metrics that we're going to use. Oh. So if you go all the way up here, so these are our metrics basically. I'm just going to clear it for now. So I'm going to explain what R squared is. R squared is the value that identifies the proportion of variance explained in the output variable. So higher value is the better, usually. So if you go all the way down here is 0.98. So it basically means that by using TV, radio, and newspaper as our variables here, we can explain 98% of the variation in the sales variable. 98%, which is pretty good actually. So higher R squared value, it usually indicates stronger model. So this is one. So this is one model metric that we wanna see from time to time. We wanna just print it and see what it looks like. So let's see. Let's print all these coefficients one by one. If we had to only use radio, then this is how we would fit it. We're gonna basically only select the radio column here, and we're gonna apply it as an X variable. We're gonna select the sales column and we're gonna apply it as Y. And in the linreg argument, we're gonna fit them. And we're gonna get the predicted values. And we're gonna get the R square score here. So if we only use radio as the predictor variable, we're ignoring TV and newspaper. Our R square is 0.33. It is low. This is much lower than 98. So if you come here, if you only use newspaper, our R square value is 0.05, which is pretty bad. But if we use all of them all together, then we get the R square value 89. So you're gonna notice that this value is different from this value. This is primarily because of the packages. So one package, the way it fits it, basically different from this package, this stats model formula API. So these two are different packages that fit the line. And one finds this value, the other one finds this value. But 89 is also really good. So this says that we are able to explain 89, almost 90% of the variation or the information in sales by only using TV, newspaper, and radio columns. So what is really important here is the formula. So I'm gonna basically write the formula by hand here. So if you remember, we had the intercept value. So we don't have the intercept value, but we can still write the formula. So this is our first coefficient times TV plus the radio times radio plus news value times newspapers. So basically this becomes our model. This is all equals to Y. This becomes our model. So let's say if we have 100 unit TV sales, 100 unit radio sales, and 100 unit newspaper sales ads. What would be our sale amount? So that's the question. 100 unit TV ads, 100 unit radio ads, 100 unit newspaper ads. What will be the sales? So given the formula, we can calculate that. We can come here, we can cut this, copy it and paste it here. Instead of TV, we can put 100, radio 100, and newspaper 100. So based on this model, if we spend 100 unit in TV ads, 100 unit in radio ads, and 100 unit in newspaper ads, this will be our predicted sales value. So that's the idea. So that's what coefficient does. But this section is a little bit more, I'll say, confusing. Then because we're so I want to highlight this section here, the root mean squared error. Root mean squared error is a model metric. You can use this formula to understand how well your model is performing. So this value itself is not very meaningful here. For example, it says 12 here. 12 itself is not very meaningful. This is meaningful only when we are trying to compare one model to the other model. So the idea of root mean squared error is this. So basically, we have a regression model, and we have a line here, right? Let's say we have a value here. We have a value here. And we have a value here. So these are our actual values here. These are our actual values. And these sections where they correspond to are our predicted values. So we are missing them, but a certain amount. So what this formula does is it takes the difference between the actual value and the predicted value here. It takes it, it squares it, and it totals them, divides by n, the sample size, and takes the square root. So basically, if the errors are higher in these points, if these lines are longer, our model is going to be worse. The value here, 12, doesn't mean a lot by itself. But if we had to take two different lines, for example, and if we had to compare them, then it would make a difference. For example, this is our alternative model. Let's say the other model is like this. This is our alternative model, like this one. So the errors for this model will be like this way, like this way, and this way. So errors are much larger for this line. So we're not going to use this line or this model, but we're going to use the red line, red model. So it enables, this formula enables us to compare this line to this line. basically. This is what it does. RMSE is important for model optimization usually. So in data science practice, you don't only use one model, you use multiple models, and for each model, you use multiple parameters. You can use the regression, you can solve the regression problem with linear regression, but you can also use decision tree, you can use boosting models, you can use neural networks, but which model is better than the other one? How do you know? And this is the way to know. You just take the predicted values and you take the differences for each of these models and you calculate the root mean squared error. And the model with the lowest root mean squared error becomes your best model. So R-square is important, but R-square, all other models don't have R-square value. Only linear regression has it, but you can calculate root mean squared error for every model. So usually root mean squared error is pretty much the standard for model comparison. It's not, of course, the only one. We have mean squared error. We have other metrics, but this is the most common one that we use. I hope it makes sense. The RMSE, how do you understand the performance of the model? For example, that could be a question if you want to seek a data science career. And this is how you know it in a regression model, usually. And this is how you calculate it. Let me use the mouse here. So after we know the RMSE in here, we can use the train and test split for feature selection. But I don't want to, it's going to confuse everybody, so I'm going to shift to logistic regression as everybody has some value. So has some energy still. So these are the advantages of linear regression. This is simple to explain, although my interpretation might be a little bit different. But we only have this formula here, as you can see. We are able to explain everything with a simple line of formula. This makes it so simple, the linear regression. This formula makes it so simple. The other models don't have it. The formula behind them is much, much more complicated. Your formula file might become like 2 GB even. So it can be really, really large. But with linear regression, it's just one line of formula and you explain it. And you are able to predict anything in the future. That's why it's usually used in academic settings. And this should be one of the first models that you fit, just to understand the data. Training and prediction are really fast. There is no tuning, it automatically fits for linear regression. Features don't need scaling, but it's good if you scale them. Scaling is another topic. Since we have the big assumption of linear relationship in here, a linear relationship, we are very constrained. So linear models might underperform. So for example, to be able to explain this relationship, we force a linear line here. Only one line. It is simple. We can use this line to explain a lot of things, but we have only one line. So it is one of its biggest disadvantage. We're constricted with one line. So performance is not generally competitive, but I would say it is still good. It's not that bad. So sensitive to irrelevant values, what it says is that if you increase the each number of columns, your R square value is going to automatically increase. So this R square value is going to automatically increase, but features are going to be irrelevant. For example, this is TV, this is radio, this is newspaper for sales. For example, for sales, say, I don't know how much sleep people have in the last night, for example, really irrelevant things. You can put as much column as possible, and it's going to only increase the R squared value. And it's going to mess up all these coefficients. So you must be really, really selective when you're trying to fit a linear regression model. You have to do a lot of exploratory data analysis. That's why these sections are really important here. Let me get some questions, then we can shift to logistic regression part because we're somewhat also running out of time. All right.
Yusuf, I have a couple of questions if other people doesn't have. This is Ranjit here. So the first question is, when we have multiple predictors, how do we end up with the intercept in that formula?
And that's a really good question. Let me see. So, yeah. So intercept value is, how it really understand is, it becomes another variable right here in the formula. So basically, this is scatter plot. This becomes another option here. I want to, okay, let me go there. Where was our formula? Anyways, so how intercept really works is, it becomes a value here as an intercept. It becomes just another variable, intercept, but the coefficients it's fixed to 1. No, the value is fixed to 1. So it works like another variable, but all the values is 1. So for example, if you think of it like here, so you can think of another variable here with all the values being 1. So it just takes that also another variable and puts it into the model.
Okay, so it's always 1 then.
Yes, it is always 1. Let me write this formula again. On here, for example, on this one, it's not allowing me to edit. Okay, I'm in the wrong one. Okay, yes. I was in the wrong notebook. So here we just add, for example, for the intercept value, let's say it was 0.5. It becomes the intercept value, and intercept being always equal to 1. So it takes it just like another variable.
I see.
But the data values becomes 1. That's how it really understands it. It doesn't fit very well in the context of multiple scatter plots, but those scatter plots are there to explain the model, to visualize the model. But when we have multiple models, we don't have those scatter plots anymore. We only have one single line of formula here. What it really does is it changes all these coefficients again and again in the model. So we have 4 coefficients here. So model tries multiple coefficients. So basically it increases here by 1 point, decreases here 1 point, increases here 1 point. For each change, it calculates the RMSE. So for each of the changes, it calculates the total error in the model. When it finds the minimum error, it stops fitting the line. So it doesn't quite work like a line when we have multiple models, multiple variables, but that's the general idea. So what other question you have?
One more is, so here you have some initial set of data that you have 200 rows and then the 4 values, right? So based on that, probably the model might have come up with that coefficient for each predictors. But in the real world, the data keeps varying, right? So how does that correlate to the model?
So in the real world, we have multiple variables. Is that what you're saying?
No, not just that. So first time, probably when you're generating a model or running this model, you started with this 200 rows of data, right?
Yes.
But that's not the case always. Today you have 200 rows. Tomorrow, as someone was asking here, they have a new media added, or for the same set of data here, you might have different data points captured going forward. So how does the model behave at that point?
Yeah, the standard behavior of the model is as the sample size increases, model only becomes better. So if you introduce data from multiple streams, then the model learns better. So model only becomes stronger. So we have 200 now. If tomorrow if we have 300, which is really good. So if we have 300,000, awesome. So so larger data is usually better. So 200 usually is pretty low number. So you shouldn't rely on a model that comes with a 200 sample.
And at that point, the coefficients are calculated automatically then?
So you have to go through all this process again when you have new data. So it doesn't do that. You have to go back. You should import all the data at once, as if like you have never fit a model before, and you have to fit it all together. So you have to repeat it. So as the new data comes in, you have to fit the model again and again.
I see.
So there is no way to tweak it here or there. Usually, this is not a big problem in linear regression, but if you're running neural networks, it takes hours to fit a single model. And there's always new data coming into deep learning models, and you have to fit it all again and again and again. So it's a really hard process. That's why autopilot is not there yet, because it takes a lot of time to fit the model.
So when you say fit the model, fitting this kind of graph, right?
Fitting model is getting this formula. What I mean by, so the perfect formula, so the best formula, the magic that we have here, this kind of formula. The formula is really simple for this one, but usually it's not this simple. So you get this formula. Once you have it, once you know all the relationships and patterns, you can start estimating all the future values. For example, in here. So once we have the formula, once we fit the model, we can apply new models, new values to it, and we can come up with a predicted value. So that's the entire reason we are fitting the model, just to estimate the future the future data points that we don't know the outcome. So we have customer data. So if we gave certain promotion, we know that customers bought the product. So we have multiple data points. Once we learn that, we can attract future customers by using those kind of techniques. Say, for example, if we give $100 promotion, then if the customer buys it, if we learn it, if the model says that this is a really strong predictor, we're going to use that information in the future, and we're going to attract future customers by using that information. So the formula basically tells us that. So if we use this one, that one, this one, this is your predicted score.
I see. Is that what called the training set?
Yeah, exactly. I skipped that part, but we can touch it just a little bit here. So this code here. So we can split the data into training and test. So basically what it does is it cuts the values. So if we do so 150 of them is put into the training set, and 50 of it is put into the my test. What's this? So we can split the data into two. 150 of them goes to X train, 50 of them goes to the X test. So in real world, we know the X train. X train is basically the predicted variables, and in this case, these are our advertisements on TV, radio, and newspaper. And we know the outcome, Y train, the sales data. We know it in real world. And we know the X test. We know how much are we going to spend on TV, radio, and sales, but we don't know the outcome, the Y test. Y test is missing, usually. So let me explain it here. So let's say 1 or 2 is our test data. If these were the test data, we never knew the outcomes here. So 22, 10.4, those values will be missing in our test data. So we will fit the model with these 3 values here. We will come up with a formula, and we will estimate these sales values. Just, yeah, it's a bit. Let's shift to logistic regression, then I'm gonna give more explanation on this topic. Is that all right?
Yeah, thank you. Please carry on.
So basically, if we have new predictors, then we would have to open a new column here, just like the internet, and that will create additional coefficient. Just to answer Udaya's question. It will be just additional coefficient value, but we would have to fit the entire model again with the additional information. So whenever the additional data comes in, we have to refit everything. So let me open this one. So basically, if you remember from the first example, logistic regression is all about estimating the class of the output. So in this case, the problem is a little bit different. So we are trying to predict if the outcome is going to be 1 or 0. That's all about it. So let's import this data and look at it real quick. So what we did is the assorted is going to become our outcome variable here. So we had multiple class types here. We have 7 of them. For 1, 2, 3, 4, we assign it to 0. For the rest, we assign it to 1. Let me fix the charging problem real quick. Yeah, if you look. So basically, so this is our glass data. This is our data set. But this is what the data set looks like. Glass, and this is what the data set looks like. So we have this glass type here. If we say glass type dot value counts, this is all the values that we have here in glass type. So if we come down here and we take all the values and we recode it into another variable and we call it assorted. Assorted becomes either 0 or 1. So if I come down here, plus assorted dot value counts, and these are the values, either 0 or 1. So for assorted type, we have 51 of them, and for the other type, we have 163 of them. So what we're trying to do here is that we're going to take all these values, columns. So these are different features of the glass. And using all this information, we're trying to estimate whether the glass is assorted or not. So it's a whether question, whether it's this or that. So we're going to import our logistic regression here. So what it does is it takes the value, it only uses L as the predictor column. L is here, only this one. It fits the model and it predicts it. So basically, this is our predictions. This is our predictions here. So given this data, it predicted all these values. So what we can do is actually this. We can do we can create a new column equals this value. We can print the glass. Okay, so if we look at here, so this is our asserted column, this is our actual value, and this is our predicted value. As you can see that only using L, we were able to correctly estimate this guy here, this section, this glass. So actual value asserted is 0, and our estimation is 0, which is good. That's what we really want. So if you go all the way down, for example, the actual value is 1 here, but the prediction is 0. So what happened is the model gave an error. So we were not able to calculate it correctly. It is 1 and the outcome is 0. Again, in here, it is correct, but this is wrong. Again, these are all wrong. So what we can do is we can create a column here, additional column, and we can calculate how much of these values are the same. So it's going to basically create our accuracy score. So this is glass assorted. Let's say if we go down here, equals so some of them are false here. If we take this value, so this is a trick, multiply with 1. So these are all correct. And if we take the mean value of this one, this is our accuracy score. So what happened here is that I compared these two columns between each other, and I calculated what percentage of them are the same. So given 0 is 0, 1 and 1. If these are not the same, then I calculated a Boolean variable here. Then I took the average of it. Then it showed that 86% of these values are the same. So basically, this is the performance metric in the classification models. So remember, we had RMSE in the regression model. But in logistic regression, we have accuracy score. So which percentage of classes have you predicted correctly? That's the general big question in logistic regression. So we're gonna come down to how it really works on the background in just a second, but is it all clear for now for the logistic regression part? So we only use L and we predicted the assorted. We only use 2 variables. And these became our predictions here. And we basically compared them on here. So we have basically functions that does all of it. I only did it for just to show you, just to give you a really quick information. If you go down all the way to the bottom, we have actual functions that does all of it. So if you remember from the Excel file, this is what it really looks like. So you take L, and you scatter it with assorted. For example, assorted becomes either 0 or 1. The L values are here. And this gives a S-shaped figure here. So what it really does is, on the background, what logistic regression does is, see, it basically cuts the value. These are all probabilities right at this point, 0.5. These are all probability scores. If the probability is above a certain threshold, let's say all these predicted values, it forces them to 1. And it forces all these to 0. So in this case, all these values here becomes 0. All these values on this section and this section as well. These values become 0, and these values become 1. Although it's not the case, what happens? So these values are 1, and these values are 0. So it fits a S-shaped probability line instead of a value line like the linear regression. It fits a probability line like this one, and it forces the values to be either in one of the sides. So basically, so if you look at it here, if the L value is low, then glass type is you can estimate that. You can say that looking at this graph without even looking at the values or anything. You can say that if the L values are low, then you can estimate that these are not assorted. If the L values is high, then you can say that it is actually, it can be estimated as 1. But what is the cut point? What is the cut L value point? And this basically gives us that. So this line, this value, whatever that might be, is our cut point. So the probability of being 1 increases all the way up to 0.05 here. So after this point, it increases, it goes beyond 0.5. If anything is 0.5, then we estimate it as 1. Anyway, that's a general idea. And this is what the probabilities actually look like. Let me Leave everything for now. Go back to mouse. So instead of classes, if we can predict the probabilities, the actual probabilities, we can predict the actual line. So if you remember, the line actually looks like this. So we have this and this, and logistic regression line looks something like this. So instead of in linear regression, it was straight. In linear regression, it was straight. In logistic regression, it's S-shaped. These are all probability values. And at this point in here, we cut it and we force all these values up to 1. All these values down to 0. We can change that 0.5 value later on. Right? Yeah. So these are the probabilities. So we just take these, and what model does is it forces all these probabilities to either one of these scores. Again, we calculate the probabilities here, and this is the S-shaped file figure here. But again, what the formula does is it cuts it all the way here, right here. It is very similar to linear regression. So instead of the outcome in the linear regression is the actual value, is similar to actual value. It is in the same unit. So remember, if we estimated sales and our predictions are in the same unit. So if we had 20, our estimation was like 18. So it was not much of a big difference, but unit is different in logistic regression. Our actual outcome is either 0 or 1, but our predictions are all probabilities. So this probability is basically the probability of being 1, closer to being 1. So if it's 0.97, for example, this value here, so this dot is somewhere around here. It's just a probability score.
So, Yusuf, to draw a correlation between linear regression and logistic, then in linear, we predicted the sales. So, if we convert this similar context here, how does logistic compare to that? Like, what is
Exactly. Yes, excellent question. So we're trying to predict sales in linear regression. In here, we're trying to predict the outcome, like the likelihood of outcome being 1. That's our prediction. So 1 is here asserted. So outcome is whatever the outcome is. For example, for that given row here, for example, this is the row, likelihood of that row, that class being asserted. So in here, for example, in this value, so in this row, there is a 98% chance that this row this class is asserted. So this is a pretty high value. We're gonna force this to be 1 in our prediction. So since it is above 0.5, we force it to be 1. But if you look at this value here, it's only 0.19. So it has a really low likelihood of being 1, or this class has only 19% chance that it is asserted. Since it is a really low probability, we just say that it is 0. We estimate that it is not asserted at all. Then that's how we convert it back to the original the label, original data type. It force it to either 0 or 1. So does that make sense?
Yeah, it does. But let's say if I take the similar data set that we took for the TVs and the sales in the previous linear regression. So for TV, we said, let's say it's 17 or 18. That was what the linear regression calculated. And so in this model, once we say that the TV sales is 18, this model asserts that 18 is 1 if that value is absolutely true as 1. Is that what the correlation?
Yeah, good question. So there's a difference between classification and regression. So for this type of problem, the outcome is either 0 or 1. You cannot use linear regression. So you cannot use sales as the output value in logistic regression. It's going to be really, really wrong. So you never use sales as the output variable in logistic regression. So your output has to be a classification type of variable. It should be whether this or that. So it should be whether, for example, white or black. That's it. No gray in between. For example, you admit patients to the hospital, right?
Yeah.
So if you're predicting whether the patient is going to die within next week, that's a weather question, whether it's going to die or not. It's a weather question, white or black, 1 or 0. That type of problem, you can apply logistic regression. But if you're trying to estimate that how much that patient is going to cost us as a hospital, for example, like say 80,000 or 20,000 or 10,000 or even 1,000, that becomes linear regression problem. So for that type of problem, we apply linear regression. It's a really important difference between linear and logistic regression. We have two very different type of data sets, very different. One is either 0 or 1. The other one is a continuous variable. It can take any value for continuous variable for the regression problem. It can take any value.
I see. Got it. Thank you.
Does it make sense?
It does. So maybe the data points also would vary accordingly then. For logistic, the data points are different, or the training set is totally different than what we have for the linear regression.
These are totally different. You cannot use classification models for regression type of problems and regression models for classification type of problems. You just cannot use it. You're gonna make a huge mistake by using it. So before you start any modeling, you have to understand the data. You have to say, okay, this is what I'm gonna look at. So this is my problem statement. Then you choose either classification or regression model. Then you continue from there. So since we are estimating whether the glass is assorted or not in this case, then we use logistic regression. We knew that the outcome is either whether, it is whether 0 or 1. But in the previous problem, we knew that we wanted to estimate sales. Sales is a continuous variable. And in that case, we cannot use logistic regression, then we use linear regression. So the problem informs us, really.
Thank you.
So the outcome of the model is a probability. So this is the math behind it, but I don't want to confuse you. So all it really says is that the outcome of logistic regression is a probability. So just like these ones. So every time logistic regression or classification models makes an output, it actually outputs a probability. So this has a really low probability. So then we say, for example, this is 0. You can use these probabilities as is. For example, you might just want to use it like that. You might want to say that, okay, well, patient is going to come in. Instead of saying to the patient that you're going to die within next week, you're just saying that, well, you know, it's not either you're going to die or not, but we believe that there's an 80% chance. So we're going to be able to say 80% because of this type of output, the probability output. So we have incoming patient, and we can estimate only the probability. We always estimate the probability, then we force all these probabilities into certain categories. In neural networks, we have multiple probabilities, and we force them in a certain way, but probability is there for every classification problem. Every classification problem gives you a probability outcome, not just a class outcome. We just force all these values into certain categories. Instead of choosing 0.5 in here, for example, in here, you can cut it all the way here. You can say that, okay, my threshold is going to be 0.8. Then I'm going to say only these people, code only these people as 1, and the rest of it as 0. You can say that. You can change threshold. It is hyperparameter tuning there. I wanna take one question, then I wanna shift to decision tree. So train test split is gonna make more sense in the afternoon. But for now, just make sure that you understand the difference between classification problem and regression problem. These are two very separate type of problems. So just to give you one more example, let's see. For example, you have an incoming customer and you're selling a product. You want to know whether the person is going to buy the product or not. You use logistic regression, for example, whether the person is going to buy the product or not. Then the outcome will be 0 or 1, either buys or not buys. If you're trying to estimate how much the customer is going to spend in our store, how much they're going to spend, they can spend $0, they can spend thousands of dollars. That becomes a regression problem, and we use regression type of models for that one. So two basic differences, two really big differences. Logistic regression also has a really nice output like a linear regression, and logistic regression has a similar formula statement like linear regression. If we have time at the end, we can come back to this, but let's go over to decision tree for now. Okay, so we are in the decision tree folder. We're going to right click it, open it, and collaboratory. So this is our Python notebook. I'm in viewing for setting. So I click on open playground, open in playground. It opened it, but it's not connected yet. So if I try to run it, it's gonna connect. I say yes, then I'm connected. So decision trees can be used for regression type of problems and classification type of problems. So this is pretty good. You can take decision tree and apply it to both type of problems, but you should be using the right package for decision tree. If you're gonna use regression, you should import the decision tree regression library. If you're gonna use classification, you should import the classification library. So you should know that you're gonna use that. But the idea, the model, the idea is the same for both of those. So in this case, we have a regression problem. We have players, we have all the stats, and we have the salary. So they make certain amount of money, and these are their stats, and we are trying to estimate how much, what are the factors are affecting their salary. Usually we expect higher performance players to get paid more, but is it really the case? We're gonna look at it. We're gonna drop some values. So what here, we dropped the missing values. If you look at here, the seller was missing. So we dropped all this row altogether. So these are basic stats, minimum and max values. These are the distributions. These are all for data exploration purposes. Okay, so I wanted to come here. So for example, let's say we only use two variables. So number of hits. So number of hits are really important, and years in the league. So how experienced they are. We have these two types of information. We do a scatter plot, and the third dimension here is their salary. So high salary is red or yellow. So yellow, red here. We have some yellow here. Low salary is blue or green. So blue and green. So if you look at here, we have this red dot here, and we have these dots here. So when we ask the model to classify this, model cuts it into three, like this one. So it says that, okay, well, I'm looking at this one and I see three regions. So one cut point is, so decision tree works always in terms of cuts. So it takes the value, and it cuts it from the middle. For each of these values, it creates another branch, like this one. For example, this here, and it cuts them at a certain point, and it grows the tree until each of these tree nodes are pure. So what it really does is it categorizes all these samples into unique categories. It just keeps cutting it. If we let it go, it's just going to create all kinds of different regions here. This region, this region, this region, this region. It's going to keep cutting it. So in this case, we only cut it by 2. So our first cut is here, years in league. So we have years in league as the starting point. We cut it. If it's below, say 4, if it's below 4, it goes to this category. If it's below 4, it goes to this category. Let me delete it. It goes to this category. But this category is not very unique. If it's above 5, then we cut it also to 2. If it's above 5 in years in league, then we cut it into 1 category and 2 category. So basically we have number of hits as our starting point. So if this below, say 4, it is region 1, for example. In this case, if it is, for example, above 4 for the number of hits, it's region 1, then we put another if statement here. Then if years in league, say above 120, it becomes region 2, for example. Let's say this is the 2. Oh, it's gone. So if years in league below 120, then we put it into region 3. So we have a decision tree. It looks, the formula looks something like this one. So it's not like it is not like linear regression. The formula is so different. It is all about decision trees. It looks very, very similar to if statements. So if you're a software developer, or if you have used any sort of software before, so we always use the if statements, and the basic idea of decision tree works like if statements. So it keeps cutting it. It keeps cutting, and it creates all these kind of unique categories, all these unique regions, and it learns that. It learns that, okay, these are my unique regions, unique leaves. If anything falls into that category, in the future, it estimates that as that kind of output. For example, in this one, this is in region 1. Let me say this is region 1 here. This is region 1. This is 2. This is 3. We have, for example, we have 3 regions here. For the 1, we can say that they are not paid so well. So if anything falls in this category, we're gonna estimate the salary as being really, really low. So if we had a classification problem, we will say that they are underpaid. If we had a regression problem like this one, in the regression problem, we just take the mean of all these values, and we say that, okay, anything falls into this category, we just assign it this value. So in this one, this is different. For example, let's say these are overpaid people. So if they fall into this region, we say that they are overpaid, or they are paid much more, or we just assign that, okay, we estimate that they are paid around like 80,000. So this is another category. This looks very similar to this one. If anything falls into this category in the future, we just say that, okay, these are also underpaid. So this is decision tree. It just keeps cutting it until everything becomes pure. I want to really go all the way down. I'm just going to run all the cells. So there is a formula behind how it really calculates the cutting point. It's called eigenvectors. I want to show you how the tree looks like. Okay, so this is what the tree looks like. For example, so this is the Titanic data. You can just click here, runtime, and run all, and you can scroll all the way down here just to see the output of decision tree, how it really looks like. So you don't usually look at this output, you just fit it, and you just predict it. So in like this statement, we just fit it, and we just predict it in the future. So this is decision tree cost 5, for example. We just use it. But just general, I understand the idea of decision tree. So if it's below, for example, say sex, it is either 0 or 1, if you remember. Sex is just a gender. If it's true, it goes to this branch. If it's false, it goes to this branch. So when it comes here, it asks another question. For all these samples in this branch, if the samples, n of the samples are below the age of 6.5, it follows this branch. If any of the guys are above, if it's true, if it's false, it goes here. So if they're below 6.5, it goes here. It's above 6.5, it goes here in this branch. It just keeps growing all these branches. So at the end of the day, what you really look at are all these different sections in here. So in this branch, we have only one sample. In this branch, we have 78 samples. So with all these decision factors, we have a subcategory here. So we can literally create an if statement and say that if anything in the future falls into any one of these categories, we just basically follow the branch all the way up. We just follow the branch all the way up. Okay, let's say the future thing is here. We just follow it here. Then we follow it. Then we come here. Then we come here. Then we make our estimate. So this is what decision tree looks like. What random forest is, it takes random number of decision trees. It selects, for example, in this statement, what random forest does is it just selects all these random rows here. Let's say it selects 1, 2, 3 this time. It selects name, sex, and age for one decision tree. Then it fits that and it makes a prediction. Then it selects next time, it selects survived P class and it selects random rows here. And it fits another decision tree. It keeps fitting all kinds of different kinds of decision trees. And it assembles them. And it makes a prediction. So this is the idea, but essentially shifted it a little bit more faster. Okay, so if you come down here in this cell, this should be where you should start. For Titanic data, just find the Titanic data. And this should be the starting point. We try to understand the decision trees. But before we go, I want to take a couple of questions. I want to quickly go over how we fit it, how we import it. Then I think it's going to be the lunchtime after that. We're going to extend this time only by like 10 minutes. And we're going to go. So if we import this Titanic data here, so this is what the Titanic data looks like. We have passenger ID. This is our outcome, whether the person survived or not. And these are all kinds of other information here. We basically recode the data. We just prepared the data for the analyses. We select the predictor columns as X here. And we select the outcome as Y here. This is a really standard procedure in machine learning. You just identify your predictor values and your outcome variable. You just apply it. Then you import the model like this one in this statement, and you fix the model. You specify the model. Okay, we want maximum depth to be 5. Maximum depth is number of rows, branches we're gonna grow. If you look at here, it's 1, 2, 3, 4. 1, 2, 3, 4, 5. It grew all the way up to 5, but anything beyond that, not anything beyond that. Otherwise, the model would be too complicated. Just to make it simple, we specify it as 5. Then we fit the model like this way. Then we visualize it. Then we had to predict anything in the future. We use this model from then on. We already fit the model. For example, so okay, we already fit the model. Let's say we want to predict something. So this is what the input data looks like. This is our input data. Let's make it put here. For example, let's say the P class will be 2, sex will be 1. Let's say for our estimation, let's say for 20, whether the person is embarked is 0. And let's say it is 1. We have all these values, for example, as our predicted values. We can go up here. We can use this one. We can do predict. We can open it. We can use these values for this type of person. Then we will predict it. Okay, so for person, so person who is in the second class, and the person sex is 1, person's age is 20, person is not embarked on Queensland or somewhere. He's embarked in this location, I think Southampton. For this person, we estimate that this person is not going to survive. It is 0. This person, we estimate that is going to die. This is our model. This is how you would fit a decision tree classifier. This is how you would specify all these independent variables, and that's how we would apply it. We extended the time just a little bit. We didn't have a lot of time for hands-on for this section or logistic regression, but I believe we can find some more time throughout the day to go back and look at all these notebooks. But just to give a shortcut, what is really important, aside from understanding the model, is to identify all these variables here, like this way. It's important to fit them in a statement like this one in Python. And it's important to predict them in a statement like this one. So this is a really standard procedure, and you can apply it to all kinds of other models as well. I can take questions, and we can take a break. Ranjit, no more questions? Already tired? Ready for lunch?
Yeah, I think it is fine, but maybe once we start looking at the real world problems, this might get a lot more questions.
Just to say, so logistic regression and linear regression, they covered in a semester.
I see.
So this is a semester length topic, and they don't even cover decision trees.
Oh, okay.
So when they cover it, they usually squeeze it to a week.
Oh, okay.
Or 2 weeks. So they spend a lot of time in all of these just to explain it and fit it. So this is a lot of content, but from this exercise, I think what you need to remember at the end of the day is the basic logic.
Right.
Basic logic of logistic regression, that curved line, the probability as an outcome, the straight line for linear regression, and for decision tree, all those decision points where we just basically cut our data into a certain point, and we basically put them into certain categories, and we build all those if statements. Then we decide based on those. So those are the main points that you might want to remember. But as you exercise and do more exercise, it's going to make much more clear in the future.
Right. Yeah, but this is really helpful to get at least understand the jargons, and then be able to look at the problems and identify which model is useful or not.
Yes, absolutely. So first question will be to answer is what kind of problem you have. So if you don't mind, so where are you working now?
Oh yeah.
Do you have this type of problems? Yeah.
We do, yes. I'm actually part of a big data team, and I'm a technical lead in AAA. So for some of the use cases, I'm on the technical side, on the data engineering side. So I do have a data scientist crew who always talks these things. At times I get confused or not clear of the point. So that's the whole idea for me to have here to be able to understand under the hood what they entail. I believe we are currently using only the we are currently using logistic regression in some cases and the linear regression. We haven't used any of the other models yet.
Okay. Yeah. This is a really good beginning
Yeah.
for models. But I hope it makes logistic regression and linear regression a little bit more clear for you.
Oh yeah, definitely. Yeah, it made sense, and then it also helped me correlate to some of my projects that I'm with in the company.
Yeah, absolutely. So notebooks are there for you to explore. I think you're gonna only learn once you sit down and go through each of these lines one by one
Awesome.
by yourself. But explanations are there, the resources there. You just take it and just apply it, and hopefully it's gonna make more sense.
Great, thank you.
And any more questions, please? Any comments?
It is really helpful actually. I didn't know decision tree before. I think it is a lot more clearer.
Decision tree, logistic regression. Yeah, these are regression type of problem. Like logistic regression is one approach. Then decision tree is a whole another approach. Once you understand it, you can also understand, for example, the boosting models or random forest or decision tree based models. You can understand them better. So there are really huge advanced versions of decision trees, but to be able to understand those, it's good to understand decision tree. And for example, neural networks is a beast, is a huge algorithm, and at this very core, very core, it is actually a logistic regression problem. So it is thousands and thousands of different kinds of logistic regressions coming together and creating one algorithm. So once you understand logistic regression, you can build on it, and you can also understand neural networks. So it's a really good starting point there. And in the afternoon, we're going to have k-means algorithm. It's a clustering algorithm, and we're going to have KNN. Also neighboring based algorithms. So once you understand them, you're going to extend your perception altogether, and you can build on those as well. So
yeah, it's really helpful. I think really, it's got a better understanding of the purpose of the decision tree. I initially viewed decision tree as a simple, basically you're making a small tabular and then doing yes or no, this kind of thing. But I didn't, after going through this class, I understand that how deeper understanding of this decision tree is for the future. All the other models are evolved from this.
Yeah, absolutely. So many different models evolved from decision tree. It is so interesting.
I appreciate that. Thank you.
Any other comments, questions?
Hi, Yusuf. I'm back. Hello, everyone. I'm Engin. I'll be teaching in the afternoon. I partly joined the morning's conversations. I need to take my car to the service so I was listening, but I wasn't able to contribute anything at all in the morning session. So Yusuf, are we going to take a break, or are you guys keep going? I see you are doing the decision trees.
We just finished that. Then we're gonna. I think everybody got a little bit tired and hungry. Take a break.
Oh, okay. A neural network, which is awesome. So that'll be great. Udaya, we were introducing our audience to each other as well.
Okay. I was working with Accenture in their digital platform, but recently I've been working on the prospector for the CMS network, Center for Medicare Medicaid, and in the ETL area. But before that, I have taken some data science workshops and materials been through, plus Coursera. So, but mostly it is in the data analysis, and didn't work as a data science project, more feeding data into it.
Oh, I see. I see. Yeah, that's the most sometimes the challenging part actually, right? That feeding the right data or getting the right data for the data science model or application. Anybody else back yet? We heard from Udaya, Padma. I guess Kash left. Did he? Should we get going, Murali, or wait a little bit?
We can get going.
Okay, awesome. Let me start sharing my screen. Okay, hope I can manage this one. I tried to put lots of interactive tools together just to give you an oversight. To begin with, I want to test, I wasn't able to put the notebooks into the Google Drive, so I put them into my GitHub page over here. You should be able to just click on it. If you go to my GitHub page, github.com/Engin Kapti, eCapti/guild datasets, you will see 3 notebooks over here. Should be 4 actually, maybe you should renew. Yeah, the PCA is here. So when you click on it, it will say open in Colab. And you should be able to reach the notebook. So if you can, guys, just give it a try to make sure that it's working, then we're good to go.
What is the repository name?
Repository name is Guild Dataset. Let me show you this one. Guild Datasets.
Can you ping it in the chat window?
Yeah, sure. How do I go to chat?
Oh. Can you share the full path? It up.
And it started to rain a lot in here in Dallas. Are you guys all joining from Dallas?
I am from Dallas.
From Maryland. It is sunny today.
Oh, no.
Pouring heavily in Dallas.
I'm sorry, I couldn't catch the last one. Did you guys able to open it?
Yep.
All right, okay, let's begin. So what I'm going to do is first try to give you a little bit of insight with the KNN. So we're going to start with the KNN. KNN is actually a supervised model, just like the Yusuf's topics, you know, the linear regression and the logistic regression. Are you guys familiar with the difference between this supervised and unsupervised learning? Little bit of. Basically, in unsupervised learning, you don't have the label, right? You don't have the outcome. And so you're trying to find clusters within your data set. But with the supervised learning, you have the outcome, so you're trying to find the patterns in the data set so that you can apply it to the new data set. So let's begin with the KNN. Can you guys see it?
Yes.
All right, awesome. Sorry, my first time trying with the iPad. So let's say that you have a couple of data points. Okay, so these are the red data points. And let's say that this is the X1 scale and this is the X2 scale. Okay. And you have another category over here. A couple of data points over this side. Okay. So what KNN does for you is when you have this new data point, the yellow point, it kind of tries to predict, you know, should it be red or should it be green? And how it does is basically it looks at the distance to the nearest neighbor, and the name comes from there. The K nearest neighbors comes from there. You know, the K means how many neighbors should I be looking at? In this case, for example, if we are looking at the one nearest neighbor, right? So the distance to here is much shorter distance to this data point. So because of this, we will say that, hey, this point is actually belongs to the yellow, I'm sorry, the green category. So this is how it tries to classify the new data points. So how does the KNN, you know, accomplish this job? You know, how does it decide? So the very first thing you need to do is choose the number of K, the neighbors, and then choose the number of the K nearest neighbors of the new data point according to the Euclidean distance. So in this case, for example, we are choosing 1. And once you choose the new data points, once you choose the neighbors and try to find the nearest one, you're trying to, the next step is to look at the, among the K neighbors, count the number of data points in each category. And then assign the new data point to the new category where you counted the most neighbors. And then your model is ready. And just a little bit of Euclidean distance insight. Euclidean distance is the, you know, the direct distance between the two data points. Let's say you have P1 and P2, right? And you have the X category and you have the Y category. And then let's say the P1 is here and the P2 is here, right? So basically you are looking at the coordinates of these two guys. Sorry, my drawing is terrible. And this is X1 and X2, and here you have Y1 and Y2. And basically you are looking at the distance between them. And the formula for that is, the basic formula of the Euclidean distance is the square root of x2 minus x1 squared plus, maybe we should draw it longer, and y2 minus y1 squared. So this gives you the distance between these two data points, the P1 and the P2. P1 and the P2. So by looking at the k neighbors and the Euclidean distance between them, we're trying to classify our new data point. So one is an easy example. If we choose an k as, let's say, 3, right, instead of 1, we choose the k as 3. And let me clear this part a bit. And these are our clusters, two data clusters. And again, we are having this new data point, the yellow, right? But this time we are looking at the closest 3 neighbors. So who are the closest 3 neighbors? So this one, green. This one is red. And I will say this one again. So we had 1 green and 2 red neighbors. And when we count, actually it sounds like the red is according to k, when the k is 3. So this data point should be classified as the red category. So this is kind of a intuition on how the KNN works. So let's look at a couple of demos online. So on the internet, there are a couple of very nice tools that shows you how they work with each other, and I really like them. I generally use them when I'm teaching about the k nearest neighbors. And here's a very good website that's showing the understanding the bias and variance trade-off. I can send you the link, and you can guys check it out later on as well. So here's the link. But we're not interested in the bias variance trade-off as of now. What we want to look is this interactive tool. So in here, we have this example, an applied example, right? The voter party registration. So we are looking at the basically the Democrats and the Republicans, the reds and blues. And on Y scale, we have the religiousness. And on X scale, we have the wealth of a person. And basically, we are trying to classify based on religiousness and wealth, who is going to be a Republican or Democrat. So to solve this problem, what happens if we apply k nearest neighbors, right? So for example, here it's showing you when the k is 1. Basically, when the k is 1, you're looking at the only one nearest neighbor. So you're kind of creating these small regions on your hyperplane. And whenever a new data point enters into your model and lands off on anywhere in here, right? For example, here, then it will say, hey, this is a red. Or in this case, it will say, this is a blue. So when you choose the k as 1, it's actually a very overfitting model. It's very focusing on the tiny details that might not generalize to other situations. For example, here, right, you see this big cluster of red, but just because of, there were like 1 and 2 data points, the blues, and since we choose the k as 1, it declared this region as a blue region, right? But most of the time when you have neat data points, if they land on here, probably they're going to be actually reds. So your model will be making mistakes. So instead of choosing k as 1, you should generally choose a little bit more. And let's see what happens when you choose k higher. So here's an interactive tool. As you can see, as of now, the k is set to 1, and it focused on very tiny details into your data that will not generalize to other situations most of the time. So we should increase the k. But how long are you going to increase the k? To what point? This is the question. So here they put this, the optimal line, which is calculated with the naive Bayes algorithm, I guess. You can check on later. So this is the optimal line that we should be reaching, right? So let's see what happens when we increase the k. Let's start with 2. Okay, so it started to change the plots, the regions of those plots. As you can see, we have the reds and the blues, and we have the white areas, which is telling us that model is not actually making a very good decisions on those areas. So 2 is not a good value as well. So let's keep increasing it. So remember, we're trying to get as close as possible to this line of distinction. We want all of them, everyone on every cell on above will be the red, and every cell under this line should be blue. I don't know how that happened. So as we increase, these are the regions. For example, the darkness indicates that model is very, very, very certain that these guys are going to be red. As you get closer to the blue, the model becomes more and more, less and less accurate as we get closer, as well as this region. Again, model is not sure. It's still gonna say, hey, these are reds, but it's not sure. It's probably going to give you like 0.6 or 0.55 probability. And if you look at the data, it's because of these blue points in between, right? In between these two regions. Because of these blue points, the model is not very certain on this category. And we can keep increasing and see what happens. As far as I remember, like 30 was the optimal k in here for the bias and variance trade-off. You guys can check on later. So 20, 30, and once you increase it a lot, then even in these regions, the model starts to lose the accuracy. These regions, model is not sure. These regions, model is not sure again. Because, at this point, for just to classify this category, you're looking at 46 nearest neighbors, which is too much. So the model gets confused because when you look at this region, there are some reds. If you count like 46, you will have a bunch of reds and a bunch of blues, so it will be difficult. So this is one intuition into the k nearest neighbors, the KNN algorithm. KNN is very useful when you have the small set of data, but you need to make sure that you scale your variables, the features, because as you can see, it really depends on the distance, Euclidean distance. So if one of your feature is like the house price, which is measured in thousands of dollars. Some will be like millions of dollars. Some will be very low, and some of them are very. The other scale is very, very on a different scale. Then you will have problems. So let me find my next intuition. This is K-means. Okay, I guess that's it for the KNN. So before we jumped into the hands-on session with the with the notebook. Do you guys have any questions?
How do you decide the optimum number? What is actually the factor which considers?
Yeah, that's a very good question. So generally, what you do is you create a for loop, or most of the time for loop, that tries a couple of k points, right? You know, you start with the k equals to 1, and then you increase it k equals to 2, 3, 4, and 5, and look at what your metrics tell to you. After some point, it will not increase. And, you know, the increase will be very, very minimum. So definitely, most of the time, the best thing to do is just create a for loop and try with different case. You know, start with the 1, and then don't just try the 1, 2, 3, 4, 5, but with some like 1, 5, and 10, and 15, and 20. This will really give you an understanding of in what regions the model is performing very good, and then you can fine tune it. You know, if you see that, okay, when the k is, you know, when the k is 20, the model is performing very good. So you can fine tune it, and you look at, you know, 21 or 19 or 18. You can fine tune that, but this is generally the strategy to tune to choose the best k in this case. Most of the time, you know, you wouldn't choose a small case. As you can see, it will overfit, and your model's accuracy will be very, very low. I would say that, you know, most of the time when I try with like 20 or 30 in most of the problems, it was performing very, very good. So let's go to the k nearest neighbors. Another question?
Yeah, what would be the typical use case for this model?
For any classification problem, you can use the KNN. Generally, what I see is if your data is small, right, and if the features are very related to each other, KNN might be performing very good. This is a difficult question, you know, in terms of use cases, because, you know, KNN or logistic regression, those are all classification models, right? So it really depends on, rather than the context, it really depends on which model is performing better in your use case. So what you would do most of the time is try KNN, try logistic regression, try naive Bayes for your classification problem, and see which one is performing better and which one is, you know, easier to manage and easier to, you know, faster, and then use it. So it's really a classification, you know, model in the end. But it's like, you know, I can tell that, you know, you want, as far as I know, the KNN is memory intensive model because it's keeping the distances in memory. In logistic regression, for example, it's just keeping the weights in the memory, right? You know, if you have like 30 features, what it does is it only keeps the 30 weights, 30 numbers in the memory, which is nothing. But when it comes to the KNN, it keeps the distances, you know, between the data points, which might be compute intense and memory intense. So you never want to use KNN for big data. Are you guys able to open the notebook?
And what other factors influence the choice for KNN?
The choice, you mean?
Yeah. When do they, you know, when do they perform better?
When do they perform better? Yeah.
When they're having too many predictors, or you know.
Oh yeah.
Related predictors.
As far as you know, most of the time, if you have too many features, KNN wouldn't help you a lot. You know, lots of features, like thousands of features. KNN might not be able to help you a lot, because in those cases, you know, the data points, when you think about your hyperplane, data points, you know, come very close to each other. So KNN would have a real difficult time in terms of distinguishing the cases. So if you have too many features or if you have too many data, I wouldn't use it. But if you ask about domain specific, like health data or other kinds of data, it's really difficult to tell. You just need to try and see how it performs. But the main criteria for choosing k nearest neighbors will be the size of the data for me. I know that this is not a very clear question, and this is kind of a challenge in data science. No, you cannot know which model is going to perform very good in any case. That's why when you look at the Kaggle competitions, I don't know if you guys are familiar with the Kaggle competitions, which are data science competitions. You will see that people try a bunch of things, lots of things in Kaggle. They try KNN, they try other models, and see which one is performing better, and then they use it. Sometimes people use KNN for visualization purposes, but it's a fairly simple model. You just feed in the features. It's very easy to tune because you only have a couple of metrics. So if you have a small set of data and a simple problem, then you can give a KNN a try. All right. Everyone able to open the notebook?
Yes.
Awesome. So we're just starting with the first cell. We're just starting with the our libraries, right? Did Yusuf talk about the Jupyter Notebook? I'm sorry, the Colab, what it is in the morning session?
Yeah, he touched upon.
Oh, okay. Yeah, the main advantage of Colab is this is actually just a Jupyter Notebook. You can be running a Jupyter Notebook in your laptop. Colab, Google came up with Colab, I guess, the last year. It's really helpful when you want to try something. You see a data on the internet and you just want to try something. The main advantage is you don't have to install the Anaconda or Python into your computer. What it does, it just gives you a small machine in the cloud, right? With these specs, 12 gigabytes of RAM and disk space around 50 gigabytes, I guess, which is cool. So most of the time for teaching purposes, this is a really good tool. And also the other advantage is you can try runtime, I guess. I'm trying to see. You can try the GPU and TPU. I'm trying to remember how we were doing it. I guess it was from the runtime. View runtime was change runtime time. Yeah, hardware accelerator. You can try GPU and you can try TPU, which is cool. You don't have to own your own machine or cool setup, fancy setup. You can just try here how it works, how it performs on your problem, and it gives you like frequently asked questions. What it is about Google Drive. I'm sorry, the Google Colab. Google Colab has also its own, the snippets, code snippets and everything. And it has its own demo. So it's a very cool tool. Most of the time what I do is I keep my, sorry. Okay, we have our flash flood warning in Dallas. Yeah, this is Colab. So let's start with the KNN, the hands-on model. First, we are importing the libraries. The shortcut for the running a cell is Shift Enter. When you push the Shift Enter, it goes to the next cell. So we are getting the data from my GitHub page from this URL. I'm just saying, read the CSV on that URL. Let's look at the data set. So basically, we have the user ID, the gender, age, the estimated salary, and whether the person purchased or not. Well, this is our label. This is our outcome. Or in academic terms, this is the dependent variable, right? You will see that you will hear a couple of wording regarding the outcome. Sometimes people say label. When you go to, when you're reading academic papers, they might refer it with the dependent variable. And then these are referred as features or sometimes the variables. So the task here is to basically try to predict whether the person is going to purchase the product or not, based on the age and the estimated salary. We're not using gender in this case. We're just using two features. And we are selecting the second and the third feature, which is the age and the salary. And then the fourth column is becoming our label, the purchase column. I'm just running it. And I'm doing a train test split. Basically, the train test split is used because, once you train your model, it can really read your data, understand the patterns in a perfect way, but you won't be able to understand how it performs on new data. So in order to try, simulate the new data, you're basically splitting your data into two sets, train and test. And you train the model on the train set and then test the model on the test set. But most of the time, people also add the validation set. So they train and then validate on the validation set, and then they try, see the real accuracy of the model on the test set. So you're actually doing 3 splits. And this is really ties back to the problem we had, the overfitting problem we had. For example, in this case, right, if you set the K1, when you train the model on the training set, it will perform very good. But when it comes to the test set, it will perform poorly. It will predict poorly because, it will think that, hey, anybody falls in here is going to be blue, but most of the time it's going to be probably red because this is, as you can see, this is a large cluster of the red. Same thing in here. Probably model will make lots of mistakes in this area as well. Just because there are 3 red points, the model declared this area as the red points. But most of the new data points in here, when you want to predict someone, if they land on here, it will probably be blue. This is what the picture tells me from here, right? So the model will be making a mistake. So with the test set, it allows you to understand these problems. So when the training accuracy and the test accuracy doesn't match with each other, you train the model, you get an accuracy of 90%, and then you test the model, and then it says you, hey, it's actually 70%. Then you say that, hey, okay, my model is overfitting, which is the problem here. Go back to the Canon. So we split our data into 2, the train and test split. And then as I told, we are scaling our features because, as you can see, they are on different scales, right? Ages, it can be 100 at most, or 130 at most. But the salary, it goes up to 150,000, and maybe, I guess the 150,000 is the highest one. We're missing some points in here. So age and the salary needs to be on the same scale, because remember, the KNN is looking at the distance, right? So if they are not on the same scale, KNN will probably focus more on the estimated salary because it will shift the distance a lot compared to the age. So that is the problem. That will be a big problem for your model. And for that reason, we need to scale our data. So we just scale the data, X-train and X-test. Let's take a look how they scale. As you can see, so this is the age and this is the salary, right? As you can see, they are pretty close to each other. Any questions on the train, test, split, or scaling?
Could you please explain that scaling?
The scaling, yeah, sure. So the scaling is just a step we do when the model is distance based. What I say is, if you have a logistic regression problem, if you have KNN, you're using basically looking at the distances between the data points, you need to scale your data, right? The reason is because, so the estimated salary is on a scale of thousands, right? It starts from 20,000, somewhere around 20,000. It goes all the way to 150,000, right? But the age, which is our other feature, is, can be between like 19 in this case, probably up to 100 something. So these are very different scales. So when you feed them into your model as is, without the scaling, right? Remember, the model is looking at the Euclidean distance, right? If I can bring my, okay, yeah. So remember, we are looking at the Euclidean distance, right? So what will happen is, if one feature is on a very high scale and the other feature is on a very low scale, most of the time, in order to predict, the model will rely on one of the features, because the effect will be much higher of the effect of the high scale feature will be much higher on the model compared to the, in our case, age. So the established salary would be much higher effective compared to the age. Because of that, we want to eliminate that problem, and we want them all to be at the same scale, between zero. Most of the time, this is, we want them between -1 and 1. So that is the scaling problem. You use the scaling again when your model depends on the distances. If you are doing a decision tree, if you are using a decision tree, then you don't need actually you don't have a scaling problem, because decision trees just cuts the data into from some level, right? Up and down, like age. It cuts from 50, and puts the values above 50 into one branch, and the values below 50 into another branch. You don't have to really scale when it comes to the decision trees. But when you are using KNN, logistic regression, and neural networks, you need to scale your features. So here we are trying to, we are fitting our model. Like we are getting the sklearn neighbors, the k-neighbors classifier. And then in this case, we are choosing the number of neighbors as 5. And in this case, the metric is Minkowski. I'm trying to see, there was this shortcut in Jupyter Notebook. Normally in Jupyter Notebook, when you do Shift Tab when the cursor is on the model, it opens up the opens up the definition of the model and then the parameters. So anyway, let's look at here. The algorithm is auto, leaf size is 30. So in this case, let's just fit it and then see how it performs, and then we will play with these features. And then we are predicting our purchased variable, right? And then we are looking at the confusion matrix. I'll come back to the confusion matrix. I just want to show you the plot first. Okay, so this is the training set, okay? So the basically model looked at the reds and then I'm sorry, there was no red and blue, right? The model looked at all the data points and then tried to classify them into the categories based on the data. And it said, hey, these are going to be the red category and this part is going to be the green category. As you can see, this is the training set, okay? As you can see, the model made some mistakes. It ignored these red points and it declared all of them as green area. Why? Remember, we didn't choose K as 1, we choose the K as 5. So we kind of handled the overfitting problem. So this is our trained model. Basically, it's just 2 areas, right? So any new data point, if they fall here, it will be, the model will say, hey, this is green, this is purchased. And if it falls over here, it will say, hey, this is red, or the person didn't purchase this product. But what happens when we have new data, right? So here we are giving the model a new data, right? The test set, and as you can see, this line is the same line with the training set, right? Actually, the model decided on this line, and here we feed in all these data points. These are the test set. This is not the training set, as you can see. For example, we have just a few points over here. In the training set, we have much more samples over here. So based on where they land on this this square, right? It says, hey, all of these guys are green, right? The model predicted that everybody on this area is green, but note that we have actually some reds. So these are the model's mistakes. The same thing on the red area as well. So any data point that fall in here, let's say you have a person with young age and low salary, right? It will land on here, and the model predicted all of them is none of them is going to purchase the product, but actually some of them purchase the product. They are green. So these are the model's mistakes. So let's see what happens actually when we do the number of neighbors as 1. So I expect the plot will be more granular. Okay, there we go. Remember the previous example, the interactive example, we have these parts. Yeah, so just like that one, the model focused on the details too much. So this will not generalize into the new data set. So as you can see, just because of the purchased dots over here, it tries to predict these small tiny points as green. So what happens when we feed in the new data? The test data. Voila. So as you can see, for example, the model said that, hey, this area is green's area. But no, it was actually, I'm sorry, this area is the red's area. And actually we have a bunch of greens, as expected. The same thing here, This is the res area. It might be catching this guy. I'm not sure. We might need to go into details. But definitely this is a mistake. And this is a mistake as well. And it did a pretty good job in those cases, actually. You know, it was actually overfitting, but really did a good job over these cases as well, here as well. But here, for example, there's this tiny red island, but our data, the test data, was actually green. So the model made a mistake over here. So this is kind of a very high-level introduction to KNN. If you guys have any questions, we can get them. Let's try to, for the last time. We tried with 5, which was okay. We tried with 1. Let's try with a higher number, like 10 neighbors, and see what happens. So as you can see, we don't have the small islands. Just this region changed a bit. So after some certain level, since this data is too small, after like looking at the 5 neighbors, you know, 10, 15, you wouldn't see much difference in terms of accuracy. So you just need to play with, you know, different settings and then see which one is performing better. Any questions on KNN? Nope. Okay, so the next is, I guess, the k-means clustering. Yep, okay. So let me turn on my iPad and let's look at the k-means clustering. So actually, k-means clustering and the next one, the PCA, these are the unsupervised models. So you don't have, for example, in this case, you have the label, right, purchased. So in unsupervised model, you don't have a label, you just have your features, you just have your data, and you try to find clusters within your data. So to give you a very high level overview, let's go back to our notebook. So again, let's say that we have X and Y scale. And we have a bunch of data points. Let's make it a little bit bigger. Yeah, okay. So you have this data, right? So this is before k-means. You just plot your data, scatter plot, and this is what you see. So what you want to do is actually try to cluster these into different categories. So for example, this one is one category. This one is another category. Oops. This one is another category, and the green is another category. So this might look very simple, but this is a very helpful model that are lots of use cases in a corporate environment. Most of the time, for example, it is very related to logistic companies' problems. You know, where you want to distribute something and you want to make sure that you're, you know, think about this as a map, right? And you want to like deliver packages into a region. So how should you create clusters on the map so that you just use, you know, like, should you use 3 members or 4 people or 5 people to deliver into these areas? It should be dense enough, right? You should have enough members in them, and so you should be using your resources in an effective manner. So actually, as far as I know, Amazon uses this when they are delivering packages with the Flex program. So basically, they create clusters of the packages that needs to be delivered, and then they send one people over here, one people over here, and one delivery person over here, so that they deliver the packages in this area and this area and this area. And this is a very nice optimization problem for most of the time. Again, like ATM, when you require home services, like internet connection or other services, basically this is a very relevant use case. So the question is, how does KNN do that? So I'm sorry, the k-means clustering. There's a big confusion about the k-means clustering in KNN, and I still use them on the wrong places. So in the KNN setting, the k is the neighbors, right? In KNN, which we just previously discussed, this is the neighbors. Right? But when it comes to the k-means clustering, the k refers to the number of groups, the mean, the number of groups. For example, in this case, the k is 3. So the very first step of the k-means clustering is, choose how many clusters, and then look at the data and, select the random point, k points. So if you choose k as 3, right? Let's go back a little bit. All right. Let's delete these guys. Okay. So first you need to choose the k, right? Let's say in this case we choose the k as 3. K is 3. So the next step is, select random k points, the center, which we call centroids. So these are not your data set. This is not your data set. These are just random centroids within your data. So let's say that we have one centroid over here, and then we have one centroid over here. The second centroid is over here, and the third centroid is over here, right? And then after you do this, you assign each data point to the closest centroid. So you're basically forming the k clusters. So in this case, for example, you look at the data and you say, hey, this is the red, and these are the data points that are close to red. And the yellow centroid is over here, so these are the data points that are close to yellow. And the green centroid is here, so that these are the data points that belongs to the third cluster. And then after you do this, you update the centroid. So the centroid, for example, the red centroid comes to the center, which is kind of around here. And then the yellow centroid is updated as well, and it comes over here. So I'm explaining one iteration at a time. And then the green centroid comes over here, and then after you do this, you redraw the clusters. Since I'm drawing, it's not a very good example. I mean, the clusters would probably be the same, but let's think that in this case, for example, just because red moved a little bit to the south, let's say that, these fall into the red cluster, and these fall into the, the yellow cluster, right? And these fall into the green cluster. So basically, you update this again and again in an iterative process, and then once there's no move, then you're basically done with the k-means clustering. So let's go to the interactive session.
But question, please.
Sure.
How does it start picking up a centroid? Where does it begin from?
It starts from a random point. Yep.
And then it keeps adjusting by itself?
Yes. So that's a very good question, because depending on where it starts, right? Sometimes it it doesn't create very optimal clusters. Actually, I used this tool, but I forgot to bring it up. Okay. So while trying to find, these are very abstract things and difficult to explain sometimes. You will get a better understanding when you play with them. So in order to make it more easy to understand, to make my job and your job easier, I'm trying to find some interactive things, and I came across this Wolfram demonstrations projects, which is very cool. I downloaded a couple of projects over here, and this one is for KNN actually, yeah. So I'm sorry, the k-means clustering, I still use it wrong. So for example, these are your data points, right? We have 41 data points. And by the way, are you guys seeing the cluster analysis, right? Not the iPad screen?
Yeah, cluster analysis, yes.
All right. So we have, no, that's too much. Let's say we have 80 number of points, the X scale and the Y scale. And we basically want, obviously when there's one cluster, all of them are in the same cluster. If we increase it to 2, it say that, hey, okay, these guys are one cluster. As you can see, it's not so easy to die. In my example, it was very easy to die. There were like, okay, 3 clusters, it is so obvious. But most of the time, it won't be very easy to die. For example, I'm saying these are the 2 clusters. And then when I increase it, okay, so I pick this one as the 3rd cluster. And then the 4th, 5th, and it goes like this. $11 cluster. So the question really comes to, how do you choose, how many clusters you should have, right? You have lots of data points, let's say 300 data points, and when you look at them, it just doesn't make sense. So you look at this map and you say, okay, so how many clusters should I have, right? This is a very good question. And there are a couple of techniques. In the IPython notebook, I'll show you the elbow method, which is kind of showing you the diminishing returns, right? In some other cases, and there are other applications of k-means clustering, and Yusuf was actually using a model which is called dbScan. So that model has different parameters than the k-means clustering. So for example, the k-means clustering, when you say, hey, I want 3 clusters, it assigns any data point to a cluster. It forces the data points to move into one cluster. But I'm not sure this is like a dense enough area for me to target, right? So in other similar methods, like the k-means clustering, one of them is dbScan, you can actually play with the, how many data points should be in each cluster. You can create these constraints so that it can better fit your business problem, right? So you can say that, hey, okay, for me to form a cluster, there should be at least like 100 data points should be in the cluster. So when you say that, for example, it will just remove these data points from your data if they don't fit into cluster. It will not say, hey, these are the green category. It will just remove them all. So there are variations of the k-means clustering, and it is very helpful in specific use cases. You just need to try to, you just need to explore various methods that you can use. So let's go to the other example I have. It was, this is the KNN. I just forgot it. I'm not going back to it. And this is the PCA. I'm trying to find my, okay, there you go. So this is k-means clustering. Okay, so this is another demo. I'll just share you the link. You can check them later on. Okay, so here we have another interactive demonstration. So let's reinitialize. So in this case, for example, we have the data points. Let's say this is, I guess, oh, yeah, okay. Yeah, first of all, I want to define the k-means as the one so that we just look at the data points, right? So, and this is our data. So how does the model work? Let's say we wanted to have, for some reason, we wanted to have 5 clusters, okay? So when we started, it will just, create these random initialization spots, right? And then it will look at the distances of every data point, and it will create the first clusters. These are not optimal, by the way, as you can see. So we will iterate one time. As you can see, every centroid moved to the center of its own cluster. But since the centroids are moved, now, some of the data points will switch to the other cluster. For example, this purple is probably going to be red, or like this blue is going to be green, probably. So iterate one more time. This time, the colors will switch. So as you can see, some of them become red, and it again update the centroids locations according to the mean. And we iterate one more time. Another move, one more time. I will just, after some time, it will just, as you can see, the move become very, very small, the incremental changes, just a little. Notice the changes between the green and blue. There isn't any more changes at all, actually. So it find the global optimum, I guess. So these are the 5 clusters that you have in the end. Let's give it a try one more time with less data points. So reinitialize. Obviously, we have this data set. It's not very obvious to the eye. I see one cluster over here, one cluster over here, one cluster over here. And if we go back to the DB scan algorithm, the other method of creating clusters, for example, this is a good one. So when we do the k-means clustering, it will force every point into a cluster. Even this point will be forced into the cluster. But when you use the DB scan algorithm, it will say that, hey, okay, so this is a very dense and good area to target. So it will just exclude these data points around it. Right, so this is dense enough for whatever your business purposes, for your marketing strategy. So let's initialize this time with less, right? 3 clusters. So we need to reinitialize. Again, create 3 centroids at different locations. And after each iteration, it updates the location of the centroid and updates the clusters. So probably, you know, look at this purple, it's going to be turning into orange. Oh no, it's going the other way. So yeah, even this one will turn into purple. And we update it again and again. And it is almost done. You know, I'm clicking on it and there's no move on the centroids because they find the global optimum. So these are your 3 clusters. So how do we do it in the IPython notebook? Let's go to the k-means notebook. I'm just gonna connect again. Do you guys have any question on the interactive session? No, okay. It might be very simple compared to the other algorithms, you know, the supervised learning. So most of the time in unsupervised learning is not used at all, is not used too much. You know, most of the time we use supervised learning models. But sometimes if you need, depending on the business case, you might really benefit from k-means algorithm, very simple algorithm. So it's very, I really advise you to just take a look at the Python's explanation, the definitions for the k-means. Yeah, if you go to the scikit-learn web page for k-means cluster, you can see the parameters in here. You know, number of clusters is initially, you know, how many clusters you want. And there's the init method. You know, there you can use a couple of other methods how to initialize. So the random one chooses the k observations at random points. There are better ones as well, you know, to address the initial cluster centers. This is a smart way. You know, this was actually a question, I guess, right? You know, where does it start? So there's this method as well, which is better than the just random initialization. When you scroll down, you will see examples using scikit-learn cluster k-means, and it will give you a couple of demonstrations. You know, if you want to understand the model, I would really go to the scikit-learn first and try to look at these demonstrations. These are really helpful. If you look into this one, for example, this is the classic example of classifying the flowers depending on their petal width, sepal length, and petal length, and one other thing, into 3 categories. So we are using the k-means clustering here. So these are very, and you have the notebooks and everything here. It creates the, you know, you can download it, or you can download the Jupyter notebook and just run it, IPython notebook and just run it. It will give you a really good understanding on how models are working. Another example over here, in different use cases, you know, how it will perform in when you have unequal variance, right? So here you have small clusters, and here the variance is much higher. So you have another problem. So you will have a really good understanding if you can just visit and take a look at the codes and then read these descriptions. And this is really fun. So let's go back to the k-means clustering. We are still connected. I'm running this first cell, and then we are getting the data. Data this time is mall customers. So let's look at the data set first. So in this example, we have the customer ID, we have the gender, and we have age, the annual income, notice that there's a K, so this is like 15,000. You really need to pay attention when you're getting the data. You need to pay attention to metrics. You know, sometimes you might see these cases where you get the annual income and you think that you will get like 15,000, but you just get the 15s. So you need to pay attention to your measurement. And then there's this spending score, I guess, you know, how much the person is going to spend. So we're just getting the X. In this case, you know, we have the spending score is actually the label, the outcome. But as I said, you know, K-means is an unsupervised model, right? So actually, we are not going to use the outcome. We will just try to classify people into categories by using the age and annual income. So we will pretend that we don't have the outcome. So I'm choosing these two features. The third one is the age. I'm sorry, the third one is the age and the fourth one is the annual income. And here is the elbow method. Basically, what I'm doing is I'm trying a couple of Ks, starting from 1 all the way to 11, right? And I'm using them as my number of clusters. And then I'm looking at, so VCSS is kind of a cost number, right? So when we run this, it looks at the different clusters and it looks at what is the cost initiated with that K. So when the K is 1, you basically have too much cost and it goes down. But after some level, it just the return diminishes. So you basically, for example, in this case, you really want to choose like 5 and you don't want to go more. When you look at the KNN, the elbow method, you can apply the KNN to elbow method to KNN as well. You will again see, you know, a big decline, a steep decline first, and then the return will be very, very, very smaller, so that it doesn't work to, you know, increase the K-means, because then your model will take more time to run. So here we say that, okay, according to the elbow method, we decided on the K. You know, the initial problem, again, was to decide on how many clusters do I need. So we did the elbow method and we said, okay, 5 seems like a reasonable number. So let's go with the 5. So I said, you know, number of clusters is going to be 5. And then we are basically visualizing the clusters. You know, the yellows are the centroids, right? And it assigned into these points. So this is the cluster. The cluster 1 is red. So this is the cluster 1. And all of these belong to, the red points belongs to the red cluster. As you can see, there's like kind of a confusion around here. It's not sure. Probably if we had 6, this might be another cluster over here. And as you can see, you know, if this was another clustering algorithm like dbScan, probably it will just drop these data points because they're not, you know, they're not very close to the centroid. Or here, for example, we wouldn't even put these guys into any cluster because those are just far away from each other. And then the second cluster, the blue, is here, and this is the centroid, and it goes on. So basically, we kind of segregated our customers into groups. So based on the annual income and the spending score. I'm sorry, I said age, I guess, first, but we're just using the spending score. Yep. So the use cases, again, most of the time, when you have the data and you don't know what to do, you don't have an outcome, and you just want to create clusters. Malls, for example, try to do that. You know, they're trying to segregate their customers into different groups, and I'm sure you guys know tons of other examples, you know, regarding the clustering or segregation of your market. Do you guys any other questions regarding the K-means?
Is there any, like, suppose if it is women customers, if you want to give additional thing, like here we have 50-50 we given, right, men and women. So suppose buying pattern, is there any way we can put additional parameter or something?
Like extra features?
Yeah.
Yeah, definitely. I mean, all of the use cases over here is basically looking at two features. Why? It's easy to visualize. That's the only reason we have this very simple simple models. You will see the benefits of the k-means, for example, mostly on the NPCA as well, and I'll talk about it when you have actually more features, not just two. So okay, yeah, definitely you can use more features, and most of the time actually you will have more features. None of the problems in the real world will be this simple. And let's go to the last one, which is the PCA. PCA, let's go to my Wolfram thing first. Okay, so actually this was not very intuitive. I might come back to that one. Let's go with the, let me see this one. PCA is kind of a difficult topic to explain. It's a very simple concept, but it's kind of, sometimes it might get difficult to explain. This is neural networks. Okay, so this one. So let's begin. So sometimes, very related to the last question, sometimes you will have too many features. You know, this is a very common problem. Think about Verizon, you know, for example, you know, collecting lots of data from everything that phone does, right? You know, what is the coordinate? You know, where did the customer clicked on the phone, when they charge their phone, when their phone is closed, you know, lots of data. And these are all different features in your data set. It comes to the point that you have too many features, and some of them are actually just noise. So you want to use these features in a way by reducing the noise. And this is what called this technique is called dimension reduction. And PCA is one algorithm that does this. So this is actually a technique that removes the noise from your data. I have one other example I'm trying to find. That's really nice. Oh, okay, yeah, there we go. So there are a couple of reasons that you might want to use the principal component analysis. One of them is, as I said, the noise filtering. You just have too many features and some of them are very noisy, so you just want to get rid of them, or like compress them and use them as is in that way. And sometimes you want to use, you want to visualize your data. So you can visualize if you have two features, right? You just plug it. You can even visualize the tree. You can create a three-dimensional, like a cubic picture, and then you can visualize tree. Even maybe 4 and 5 by using the colors and then the shapes. But it really becomes very, very difficult to understand. And after 5, it's like impossible to visualize your data. And think about what happens when you have thousands of features. How can you visualize the data? So again, the principal component analysis is a tool that you can use. It will create, if you have, for example, 1,000 features, it will create 2 components out of your data, and you will be able to visualize your data in that way. So in the end, it's instead of the 1,000 feature, you will have 2 components of your data, and I will come back to it. Sometimes you the principal component analysis is used like a feature extraction. So you don't want to use all of your features, but you want to create these principal components, and you want to use just these components as a feature in your data. So these are a couple of use cases. So again, with the principal component analysis, it's really important to scale your data. It needs to be on this, all of the features needs to be on the same scale. So let's start with this example, and I hope you will have a better understanding. And again, this is a very toy data set. As you can see, we have only 2 features. So why would you use like 2 features to create 2 components? It doesn't really make sense, but it will make it easier for us to understand. I'm sorry. So let's say we have 100 data points, okay? And the row here is the correlation. So X1 and X2. For a second, ignore the yellow and the green line. These are actually the principal components. I don't know if you can show them without the without these lines, but I guess it's impossible. Yeah, it's impossible. Anyway, so you have 100 data points, okay? And X1 and X2. As you can see, these are scaled. So it might be age and salary, but now it's just scaled feature. And let's say the correlation is very low between these 2 guys, so it will be more distributed. So basically what you want to do is, compress your data in a way, in the end, you will have only 2 components out of your data. So I know that it doesn't make sense once you hear it first, but here's how it is. So what we did is, we tried to find these components out of our data by looking at a couple of metrics and correlation. And we kind of squeezed all of our data into these 2 components. So instead of X1 and X2, now we have these 2 PCAs, which are the components. And at the third graph, it's basically showing you how the components are correlated with the feature itself. So this scale is the coordinate index. This is the number of data. If I put 10, it will be easier to understand. So for example, green is the X1, right? Let's say. So the first X1 was around here, and it landed on the principal component over here. So this is like the distribution of your X. Think about you are taking this scale, okay, and like pushing it this way and compressing all of your green points and red points onto this scale. So you are really reducing the noise and the dimension in here. So I know this is very confusing, but is this at least a little bit tell you how does the PCA works? And we will have more examples, and I'm sure you will be understanding a better way. Any questions so far? Let's try with lots of data, and let's try with high correlated data. So it's very correlated data, X1 increases, X2 increases, very simple. And I want to get two components out of it. And here are my 2 components. Let's go to the second graph. It's showing me the components. Basically, it squeezed all the data into 2 components. And here's how it looks like when you distribute the X1 and X2 against the principal components. Let's go to the next example, and I'm sure you'll be understanding a better way. Because you really understand the benefit of the PCA when you move to the third dimension. The second dimension is like, you're converting 2 dimension into 2 dimensions, so it doesn't really make sense. Because the main purpose of PCA is to reduce the dimension, so you should start with more than 2, right? So here actually we can play with the data points. It's very interactive. In this case, we have these 5 data points, and it's creating these 2 principal components out of it. One of them is vertical and one of them is like horizontal, and it is converting them into these 2 components. As you can see, we have the X and Y feature over here in the original data set, but the output of this, the PCA, is now you have the PC1 and PC2, which are the components. So if I move, for example, this data point around here, as you can see, it moved down on the PCA as well. If I move it like this, as you can see, the angle of the PCA in the components are changing as well. And here it shows you where they land on the feature, the components. Let's say, I'm playing with this one. By the way, before I forgot, let me send you the link. But let's move to the 3 dimension. This is a better example. That's why my Mac is screening. So here you have 3-dimensional data set, right? So you want to visualize this, but it is difficult, and you want to get an understanding of the data on a 2-dimension. So basically, you do a principal component analysis, and you say that, hey, give me 2 components out of this. So what it does is it reduces one of the dimensions, and in the end, you have 2 dimensions, and this is the output of the PCA. Yeah, so in this case, this is the output of the PCA. You only have PC1 and PC2. So it removed the PC3 because this is the least variation in the data set, right? It used the PC1 and PC2 and just didn't use the PC3. And this is the reduced dimension you can think of. I guess we can play with the data points over here, and it affects the bottom as well. I'm not sure. Yeah, let's reset, and yeah. I don't know if we can use, yeah, we cannot play with the data over here. But I guess this is kind of a better intuition in terms of understanding how PCA works. And there are other examples in here you can play with. If there's no other question, we can move to the interactive notebook. Any questions? Okay. Do we have our participants still? Yeah. Awesome. Okay. Sorry. If you guys can open the PCA notebook.
Yeah, did it.
Is there a question?
No. Opened it.
Oh, okay. Awesome. Okay, so we open the PCA. Again, the first cell is our library. The first cell is we are getting the NumPy, Matplotlib, and Pandas libraries and reading our data from this URL. And let's take a look. What is our data set look like? So as you can see, in this case, we have lots of features, not just 2, right? We have 2 main features, and we have the customer segment. I guess this is the outcome. But we don't need the we don't need to know the outcome, right? The PCA is unsupervised learning, so we will just create components out of the data until the pro line. So we're getting the X. This is the one we are interested in, but we are getting the Y as well, just to see how does PCA performs, right? Because we will use the PCA on X, and we will create out of the 13 features, we will create only 2 components, and we will use them as a feature in the model and see how it performs. You know, because essentially we are not using all of the features, we are just using 2 components out of it. We removed some data, we actually removed some of the information. So how does it perform in this case? That's why we are having the Y as well, just to see how it works. And then again, we are splitting our data set into train and test split, and then we are scaling our data. And as you can see, we are transforming our PCA. I'm sorry, we are getting the components, and we are saying, hey, I need 2 components out of this data, X-train. So let's look at the explained variance. Yeah, so the 2 components, you know, how much variation they are explaining. And let's look at the X-train. So in this case, we only have two components instead of it's converted into an array. So we only have, instead of 13 features, we have only 2 numbers, which are, you know, this is the component 1, this side, and this side is the component 2. And then we are using the logistic regression, and we are feeding in X-train. Remember, X-train is now just 2 components. And we are making a prediction. So with just using the 2 components, as you can see, we were able to classify our target into 3 categories. In this case, we have 3 outcomes, I guess, 3 categories in our outcome variable. So we were able to, just using the 2 components, we were able to do a pretty good job. And this is the test set. As you can see, it only made a mistake over here. This should have been red, but it did a pretty good job. So one more time, instead of using alcohol, malic acid, ash, magnesium, flavonoids, and everything, color intensity, we are getting 2 components out of all of these features, the 13 features, and we are just using those 2 features into our model here. And we are still able to do a pretty good job. So what are the benefits? As I said, we remove the noise out of our data. We only have 2 features, so our model will perform, will be much more scalable, right? If it performs as good as the logistic regression. So it's very much more scalable, since you only have 2 features. You can visualize your data. You can say that, hey, okay, this is how the data looks like when you have the 2 components. So it's a very effective tool, and there are many applications. If you have lots of dimensionality problem, lots of dimensions in your data, PCA is a very helpful technique. And this is the end of my session, I guess. So I try to cut it short a bit. I just wanted to give you an overview of the TensorFlow tool and this tool. Just to give you an idea, because you really start to understand, these techniques when you apply them to problems yourself and when you think about the use cases. So what I really want to do is, kind of give you an intuition on what is available out there and what are the use cases, and at a really high level, how they work. If you have any questions regarding the KNN or K-means or PCA, we can talk about them. And then I really want to move on to these two tools I want to show to you, which are very fun to play with. So any questions? If we do one more time, a fast pass, we started with the KNN. Again, KNN is the supervised model, right? The K-means clustering and the PCA is the unsupervised ones. KNN is looking at the number of neighbors. So this is the demo that I missed at the first pass. So this is like this line, as you can see, is the optimal line, right? The blue line. So we should be able to, get something very similar to this line, these regions by using the KNN. Again, when I set the K to 1, my model is overfitting, meaning that it's focusing on the tiny details. It's missing the big picture, focusing on very tiny details. And as I increase the K, now it's looking at 3 neighbors for every data point. For this guy, for example, it's looking at this one, and maybe this one. In this case, for example, it's looking at this one, and this one probably, because those are the closest neighbors. And as we increase the K, you will see that it will get rid of these regions and it will be better generalizing into new data sets. One step forward, 5, 7, and 9, 11, 13. Now, this one looks okay. If we go more, yeah, it gets rid of this part as well. So yeah, actually 23 might be just a little bit much. I'm trying to capture this area, but it might be impossible. I'm trying to get as close as this line. This line is just a reference. In real case, you don't have any line, you don't have anything, you just understand based on the, as I said, you try a different case and you try to see how your metric, whether it is accuracy or, log loss or area under the curve, whatever your metric is, you try a different case and you see, okay, this K is performing much better, so let's use that one. So in real world, you don't have a line like this, showing you which K to use. This is just giving you a reference to understand, what you should be targeting when you're adjusting your case. So as I increase, it's running a little bit slow, I guess. Yeah. So now, as you can see, we started to just, if we increase the K too much, then we are falling under the trap of bias. So our model is not actually doing a very good job. It's just making overgeneralization of everything. Yeah. So this is KNN one more time, the number of neighbors. And let's go to the K-means clustering, which was the second topic that I tried to highlight. So again, these are our data points. This says cluster analysis, but this is really a K-means clustering algorithm. These are our data points, and let's increase the number of clusters. Actually, the other tool was a better one, I guess, the interactive one. Yep, this one was much more better. It gives you an understanding of reinitialize. let's start with one cluster and see how our data look like. Okay, so this is our data. We don't have any idea on how to cluster them. And we basically say, okay, let's try 3 clusters. Remember, you actually use the elbow method for this purpose. I mean, just using one number. Now, let's say we want to use 3 clusters, and I'm reinitializing. And as you can see, it created 3 centroids. It depends on the method you are choosing. So it doesn't tell you the method pure random, yeah. Random cluster. So this is totally random, I guess. Pure random sounds more totally random, but yeah. This is the data generation, yeah. Yeah, the data generation is random. It's not about the initialization. I was trying to show you how the different initialization methods look like. This look like, you know, getting some understanding from the data. It's not totally random, the centroids. Otherwise it would start, you know, it should be able to start like at very random locations like the corners, right? But, oh, okay. Yeah, so the initialization is pretty random, I can say. It's not learning, yeah, for example, right? It's not learning anything from the data at all. But in our use case, we were using the K++ initialization, the init method. It was not random, so we were kind of using, you know, we were making a smart decision on where should be the initial location, the initial location of the centroids should be. I keep losing that one. Okay. So the centroids are randomly initialized. And let's start with this one. I want to try actually random clustered here. Yeah, so what happens in this case, right? We have 3 centroids and we have these data points. Maybe we might force the model to make mistakes and capture that. So yeah, let's start with this one. So iterate one more time. I really wonder what's going to happen with this guy. So actually, I'm asking for 3 clusters because of the random initialization. I guess it's making a mistake. It won't be able to capture the 3rd cluster. Let's see what happens. So I'm updating one by one. So yeah, so it's not because of the random initialization. It totally missed this cluster. If you reinitialize, you know, this case, for example, it will force them into 3 clusters. And yeah, I guess it optimized. It is optimized. Yep. So this was k-means. Again, use cases are, you have your data set, you have your, for example, the best use case I use is you have your like customers in a region, in a city, and you want to send ads or you want to send people out in the field, but you want them to be dense enough and you want to know, you know, which category are they in, you know, is there, you can create a cluster out of those people out there, you know, this is a very high income region with, you know, high education levels, and this is a low income region with, you know, people in this area are generally have these kind of problems and so on and so forth. And this is another area, you know, some specific certain types of people live in. And then you can say that, hey, okay, depending on this clustering, I should really be targeting this cluster or this cluster. So there are a couple of use cases. And the last one, the PCA, if we go to this example, what it really does is it brings down, it removes the noise out of your data. It compresses your data into the number of components that you define. In these cases, we ask for 2 components. You might ask for more actually. But in the end, you know, you will get the number of components that you ask for. In this case, we have 2 components, PC1 and PC2. And as you can see, now I can have a very good understanding of the data. And in this case, you know, I think that the noise in the PC3, the distribution is very, very small. It doesn't vary that much. So there isn't too much information in the third component. So basically you have 3 dimensions, but in one dimension, there isn't so many information, which is the third dimension, which is the blue. Actually, you know, if you, this wave, right? When it comes, when it is turning, when it becomes vertical to us, like this wave is showing you the variation of the blue. So it is very minimum. So I say, okay, let's remove this one and just use the PC1 and PC2. All right. If there is no other questions, I just try to do one more pass. I like iterative learning, just like a machine learning algorithm. So I just want to give you an overview of these 2 websites. Any questions? Any feedback, any thought? Anyone there? No one? Hopefully,
It is very good demonstration of k-means clustering. So.
Oh, awesome! Yeah.
Yeah, that's yeah.
Yeah, I'm sorry. Yeah, go ahead.
Yeah, that is absolutely true. Very helpful and understanding on the use cases, and then the demonstrations are really intuitive.
Yeah, yeah. The difficult part is to be intuitive. Honestly, you know, the coding is, you know, when you get into coding, there are lots of demos, as I showed you in the scikit-learn webpage, and these codes, you know, kind of give you an understanding. You will really get used to them once you use it. But what I want to do is, you know, give you a little bit of intuition to use, so you know which tools are there, you know how they are used, and so on and so forth. So here, maybe we should start with this one, because this one ties back to other. So this is a playground from TensorFlow. Is anyone familiar with this one?
Yes, I saw before.
Awesome. Yeah, good. So this is a very nice tool. Basically, so this is the playground of the TensorFlow algorithm. You can create a neural network in here. The good thing is you have your data. You can try a different subset of data. You know, these are like different problems, and you can play with the features. You can play with the architecture of the layers. You can see how they perform a good job in different cases. And I will try to, although this is designed for neural networks, I will try to show you different use cases. For example, if actually when you do just 2 features, right, and no hidden layers, you know, the features are directly feeding into the output layer, you're actually doing if you choose the sigmoid function, you're actually doing a logistic regression. So this is nothing more than a logistic regression as of now. So the neural network, in essence, kind of a combination of different logistic regressions, I would say. I mean, they don't all use sigmoid function. Sigmoid is the function that the logistic regression uses. So in neural network, not all of the layers use sigmoid function. Sometimes they use ReLU, sometimes they use tangent. But when you simplify the problem, it's actually a logistic regression in this case, for example. And we will start from here and go into complex neural networks and how they perform on different data sets. So the logistic regression, we use it for binary classification, right? And remember, logistic regression is a linear classification algorithm. What it does is it just can create a linear separation in here, right? So let's run the epochs. And this is the output. This is showing you the loss. I started it. And as you can see, it did a pretty good job easily. Why? Because data is easy, right? You know, these are two separated data sets. And they're feeding into the model. And this is, when you hover over the feature, it's showing you that, hey, this feature is kind of dividing your categories into two, but, you know, with a bit of horizontal line. And this one is doing kind of creating like a vertical line. And when they come together, they can, you know, distinguish this two subsets from each other. So a lot of the times when you're running a logistic regression, you have some features, but you can create other features as well. And they can perform different jobs on your data. And the main purpose of this session is really to highlight that part. For example, what happens when I feed in x1 square, right? So I have the x1 and I just take a square of the x1 and feed it into the model. So now I'm able to create different zones on the for my output. In this case, do I need it? No, actually, just two features are enough for me. The log loss is perfect. I don't need an extra feature. So we need to create a complex problem than this one. So let's look at maybe this problem, right? So this is the problem in this case, and it's very difficult to use just logistic regression with just two features as is, because it will just create a one line and it will be difficult to perform very good. So let's start and see how it performs. As you can see, the log loss is very high. It doesn't know what to do. You know, it basically cannot classify into categories, right? So see what happens when I feed in the x1 square and x2 square. So again, this is a binary classification problem, so it focused on here, as you can see, and ignored this part. It is better than just two feature. You know, at least the training loss is above 0.5, but it is really missing this part. So what happens when I add an interaction feature? x1 times x2. There you go. So now, as you can see, I'm able to better classify my output. And you can even add like sim x1 and sim x2 and come up with even better solutions. But if you have a very complex problem like this one, even the logistic regression won't be able to solve your problem. You know, let's see what happens. It just doesn't know what to do. You know, when you look at the loss function, it goes up and down. It doesn't really know what to do. And if you increase the noise, it will even be much more difficult, right? It will be just, it's not even better than a random case. So in this case, actually, these are the cases when you need like other models, like neural networks or decision trees. So you really need to understand when you come across a problem, the first thing you need to do is, hey, what is the complexity of this problem? Is it a linear problem or nonlinear problem? You know, how does, you know, you should start with logistic regression. A lot of the time, the common mistake is people think that neural networks is the solution to everything, and then they apply neural networks to very complex problem, and then they cannot get an accurate answer, and they just, you know, got buried in the hole. So in this case, for example, we tried everything with the logistic regression, but our problem is too complex, so we want to move into the world of neural networks. So basically, I'm adding a hidden layer over here, right? And I can add more neurons, like 3, 4, 5. Let's start with just one neuron. So what happens is all of these features are feeding into the one neuron, and it's making a decision on the classification. And as I hover over them, you know, it kind of shows you what is the job of this specific feature. And this will really tie back very good when we go to this example in terms of understanding what is the job of this layer, you know, where is it focusing on. So let's start with, let's say three neurons, I'm sorry, in the hidden layer, and see how it performs. And this is a very complex problem, by the way. I mean, the noise is too much, and this is the most difficult problem in these toy sets. So as you iterate with the epochs, it's trying to distinguish areas, and as you can see, it's capturing this information all over the here. It's doing a pretty good job, actually, with just 3 neurons. And look at these 3 neurons. Look at how they look like. So, for example, this one is just focusing on it's just excluding the center and it's focusing on the outside areas, right? The blue is where it focuses on. And this one is focusing on the top part, and this one is focusing on the center. As you can see, the center is the place that it makes most of the mistakes, but the model is overall performing a very good job. So what happens if we give more power to the model, make it more complex, and expect it to perform better? Do we even know? And notice that all of them are sigmoid functions. It should be actually a relay something. You see the log loss model is not really able to clearly classify these 2 categories. It's not sure, so the log loss is going up and down, up and down. So model is not converging in this case. It might either need to run thousands of epochs. You can play with the learning rate, which means that it will learn faster. Let's increase the learning rate, for example, what happens? It totally messed up because it's too much. And this will, if you use the learning rate too small, it will take forever. And there's no regularization in this case, for example. Anyway, one last example. I want to look at this one. Let's remove the noise a bit because it's too complex. Yeah, this looks good. Yeah, let's look at this one. Yeah. I'm keeping the same architecture. Because the learning rate is too small, it's going to take forever, so I'm just increasing it. And look at the log loss after I change the learning rate. It suddenly dropped. But not that, if you increase the learning rate too much, and learning rate is not specific to neural networks. Any type of algorithm has a learning rate, logistic regression or anything. They all have a learning rate. I'm not sure about the k-means. I'm sorry, the KNN. But if you increase the learning rate, it will be much more difficult for the model to learn because it's making 2 big jumps over the gradient descent, so it's not able to find the globe locally. Anyway, do you have any questions on this part? You can really play with this. This is really intuitive. I really like it. You can increase the layer sizes up to 6, and you can increase your neurons and how they are interacting with each other. Basically, every neuron is feeding, every layer is feeding information to the next layer. So this layer, the second layer is feeding information into this layer. This one is feeding information into this layer. And It's not this guy feeding information to all of them. It's actually just feeding into some specific subsets. That's how it focuses on the parts of the problem. Every time it focuses on a part of the problem, every neuron. Yep. As you can see, it's even showing you the weights. And you can, I didn't know you can actually play with the weights. You know, the weight is basically showing you the relation between two neurons, right? So this is a very high weight. You can actually make the model perform poor by playing with these weights. You know, you'll never see a weight of 6,